Alrighty, folks, so can you believe it? We are now starting the final unit of Math 30-1. So 4 down, 1 to go. Okay, it's called Permutations and Combinations. Now, this one is going to feel like a little bit of a change of pace. It's kind of a nice little, I don't know, switch it up at the end of the course. It's obviously it's still math. We're going to apply a lot of the things we've talked about, but we're kind of going to go into a different area of math here where we're talking about different ways of putting things together, the number of ways things can be arranged, kind of in the world of probabilities and mapping outcomes, and the different ways different situations can turn out. So a little bit different than the functiony stuff we've gotten used to. Of course, though, a lot of the skills in math are universal, and we'll draw on them here as well. But here are the big ideas for today. Looks like a lot, but we're introducing some new concepts and some new notations and stuff today. So that's why there's a longer looking checklist than normal. But as usual, right, use this to check in with yourself at the end of the lesson. What of those do you need a little more practice with? What of those are you pretty good on? What of those do you need to ask me about? Okay, I'm always happy to help. But without further ado, let's jump into the first lesson of the final unit. Here we go. So we're going to start out here with basically just a little investigation to start to see some of the ideas that we're going to apply throughout this unit, to see where they come from, why they do kind of make sense. But we're going to start doing this by just kind of thinking about it, seeing if we can map it out on our own, and then we can talk about the math theorems and principles that are underlying it. Okay? So suppose you lay out your clothing options in the morning. You've got 2 different pairs of pants, so khaki pants and white pants. 2 options for pants. 2 options for shoes. You've got yellow shoes and orange shoes. And you've got 3 options for shirts. So you could wear a red, a green, or a blue shirt. So it wants us to make a tree diagram to map out all of the different possible outfits. So we call it a tree diagram because it has branches. It shows all the different, ways we could branch off and make a different outfit. So I'm just going to start out. Doesn't really matter the order we do here, but let's just, go in this order. Let's pick our pants first, then we'll pick our shoes, then we'll pick our shirt. Okay? So right off the bat, we've got 2 choices. So we represent that with a tree diagram like this. This is our pants. Okay, pants. Okay, we've got 2 choices. We could wear red pants or we could wear white pants. So if you think about it, we haven't built the full outfit yet, but there's already kind of 2 ways our outfit could go, right? But then from there, we could wear yellow shoes with either pairs of pants. Whoops, I don't know why I put an R there. It's supposed to be a K for khaki. Sorry about that. K. All right. With each of those types of pairs of pants, with khaki or white pants, right, we could wear yellow or orange shoes with khaki pants, or we could wear yellow or orange shoes with white pants, right? So you'll see what I mean why we call it a tree diagram, because it kind of branches out, right? We could wear khaki and yellow, or we could wear khaki and orange, or we could wear white and yellow, or white and orange. See how this is starting to look like a tree diagram? Okay, that represents our shoe choices. So notice, so far, we could have picked 2 things for our pants, and then for each of those, we could have picked 2 different shoe options. You can kind of see we're already up to 1, 2, 3, 4 possible outfits, right? Khaki yellow, khaki orange, white yellow, white orange. 4 total, okay? But we're not done, because for each of those pant-shoe combinations, we could also wear 3 different shirts. So we could go khaki, yellow, and then a red shirt, a green shirt, or a blue shirt, right? Red shirt, green shirt, blue shirt. Red shirt, green shirt, blue shirt. Red shirt, green shirt, blue shirt. Okay, so those are now representing all of the different ways. My tree diagram got a little crowded there. I should have probably just going to fix that up a bit so it's a little easier to see. There we go, right? We could have gone, again, red shirt, green shirt, or blue shirt. I won't write it for all of them, but that's the idea, right? So do you see all the possible different ways our outfit could turn out? We could go khaki yellow red, khaki yellow green, khaki yellow blue shirt, or khaki orange red, khaki orange green, khaki orange blue. Those are all different outfits. And you can see here that the tree diagram essentially shows us how many possible different outfits there are. So this is one, this is another, 4 possible, 5 possible, 6 possible, just from the khaki pants. And then there's another 6 with the white pants, right? 7, 8, 9, 10, 11, 12. So there is our tree diagram, and that allowed us to do this, map out all of the different possible outfits. So how many possible outfits are there? 12. Okay, just counting them out, mapping them out, right? And that's essentially what we're going to be doing a lot of in this unit, thinking about how many different ways can we put together or choose or arrange from a group of things, okay? Now, this can get, for some of the things we're dealing with, we might be choosing 15 different things out of 100 different options and then arranging them. So you can imagine this would get pretty hard to draw. But this lets us see the underlying logic behind what we are going to, the first thing we're going to talk about that's going to be one of our best friends in this unit, and that is something called the fundamental counting principle. Let's talk about that. So the fundamental counting principle allows us to figure out the total number of possible different outcomes in a probability problem, right? What we're thinking of here again is what are the total number of different outfits we could wear. Those are like outcomes for this situation. If you're going to put on a pair of pants, a pair of shoes, and a shirt from these options, right? How many different ways could that possibly turn out? And we figured out that it was 12, okay? So what does the fundamental counting principle actually say? What it's talking about is if, 2, or as we'll see, it could be more than 2. In fact, in this example, it was 3 things. But suppose 2 things are going to be chosen or 2 things are going to happen, right? 2 different things have an outcome. And we want to know the possible number of ways that the overall situation could turn out, right? In other words, all possible ways that both events together could turn out, right? Again, here we're doing 3 things. We're choosing a pant, choosing shoes, and choosing a shirt, right? So overall, that's 3 separate things, 3 separate events or choices. We're wondering how many ways could the entire situation turn out, right? And all the fundamental counting principle tells us, it's actually pretty straightforward. It says that if there are P just standing in for some number of options, if there are P options for the way thing 1 could turn out, and Q options for the way thing 2 could turn out, then there are a total of P times Q ways that the overall situation could turn out, right? In other words, if there's P ways to do one thing and Q ways to do another thing, there's going to be P times Q ways to do both things, right? Again, if there's 2 pants to choose from and 3 shirts to choose from, that all we're saying is that there's going to be 6 ways to choose pants and a shirt. Okay, 2 options for pants, 3 options for shirts, 2 times 3 is 6. This principle holds no matter how many things are included. So I know in this example we said thing 1 and thing 2, but if we were going to add a third thing and ask what's the overall way all 3 things could turn out, it would be multiply the number of ways each individual thing could turn out. Okay, if there are 3 events with P, Q, and R ways for each of those events to turn out, then the total number of possible outcomes is just P times Q times R, whatever those numbers are. So tree diagrams, the reason we started with this a tree diagram is it can help us see that this isn't just some magic trick. We can kind of see why it makes sense, right? Looking at the tree diagram we just made for our outfit above, we had 2 pants choices. Well, that alone gives us 2 possible outcomes, right? Just for pants, there's already 2 possible outcomes. But each of those pants could be paired with 2 different shoes, right? Each, keyword each pair of pants could be worn with 2 pairs of shoes, meaning that we have to now multiply the number of outfits so far by 2, right? Because for each of those pants choices, we can pair it with 2 pairs of shoes. So that takes us from 2 outfits so far to already now 1, 2, 3, 4, right? Notice here for each pair of pants, there are 2 pairs of shoes we could wear with it. And that's why we're going to multiply by 2. For every pants option, there are 2 shoe options, giving us 2 times 2, or 4 possible outfits already, without even considering shirts yet, right? And we can even map out what those 4 options are so far. We could do khaki yellow, khaki orange, right? Or white yellow, white orange, right? We went from just khaki and white to khaki with yellow or khaki with orange, and white with yellow and white with orange. Okay, and now the same logic, but we're going to have to multiply by 3 here, because for every one of the 4 outfits we've come up with so far, we could finish it off with one of 3 different shirts, right? So there are 3 ways we could complete our khaki yellow outfit, 3 ways we could complete our khaki orange outfit, 3 ways we complete our white yellow outfit, and 3 ways we could complete our white orange outfit, right? Giving us a total of 2 times 2. And then for those 4 possible outcomes, we need to multiply by 3, because for each of them, there are 3 ways to finish it off with a shirt, right? For each of those pants shoe possibilities, we can wear 3 different shirts, giving us 3 unique outfits for each pant shoe pairing. So we need to multiply our 4 by 3 to find the total number of possible outfits. And just like we found by mapping them all out with the tree diagram, let's see what the fundamental counting principle tells us. So there's 2 ways to choose our pants. There are 2 ways to choose our shoes. So 2 times 2. You can see that so far so good. That would give us 4 possible at this stage. And then for each of those, there's 3 ways to choose our shoes. Our shirt. So overall, that means the fundamental counting principle says to choose all 3, there should be 2 times 2 times 3. 2 times 2 is 4, times 3 is 12 possible ways, which, hey, that's exactly what we see here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's the logic behind the fundamental counting principle. And it makes sense when we think about it. If there's P ways to do one thing, then for every P of those, we could pair it with Q different ways of doing the other thing, giving us P times Q ways overall that both things could get done. Let's try out some examples here. All right, so a restaurant has a meal special. $5 will get you a sandwich, a side, a dessert, and a drink. Their menu is shown below. How many different meals are possible? Okay, so you get to pick a sandwich, a side, a dessert, and a drink. Now for each of those choices, you have multiple options, right? So let's just think about this. How many ways are there to choose a sandwich? Well, I see 1, 2, 3, 4 different ways we could choose our sandwich, right? 4 options for the sandwich. Okay. For the sides, I see 3, fries, onion rings, salad. So 3 options for the for the side. For the desserts, I only see 2, right? Apple pie or chocolate chip cookie. So 2 options there. Drinks, we could do water, lemonade, orange juice, apple juice, or cola. So that's that. 1, 2, 3, 4, 5 options for our drink. Okay, so every single one of those is going to give us a different outcome, right? If we go, crispy chicken, fries, apple pie, water, that's a different meal than crispy chicken, fries, apple pie, lemonade, right? Which is different than all of those with orange juice, or all of those with apple juice, or all of those with cola, right? So you can see why we're multiplying here. For every single choice we make, in the next set of choices, we could pair it with, 3 different options. And then for those, we could pair it with 2 different options. And then for those, we could pair each of them with 5 different options. So how many meals are possible? The fundamental counting principle says if there's, 4 ways to do it, 3 ways to do it, 2 ways to do that, and then 5 ways to do the last thing, well, multiply them together, and that tells you how many ways there are to do all of them, which is what we're doing. We're choosing one of each. So they'll just be 4 times 3 times 2 times 5, which is 120 different meals could be made from this menu if you get to pick one of each. Right? That's the fundamental counting principle. Okay, let's try this one out. In Alberta, license plates used to have 3 letters followed by 3 digits. New combinations eventually ran out, and so now license plates must consist of 3 letters followed by 4 digits. How many of these new style license plates will the Alberta government be able to make before it has to switch the style again? Okay, so if we think about, what's this really asking? It's just saying, right? I mean, when will they have to start making new ones? It's when they've run out of different possible combinations of numbers and letters, right? Or I should say permutations. We'll talk about why that terminology is important as we go, okay? But eventually we're going to run out of this style of license plate too. Might be a very long time away, but we can't make an infinite number of these, right? So let's break this down a bit. We want to have 3 letters followed by 4 digits, okay? So how many options are there for letters? Well, there's 26 letters, right? In the alphabet, A to Z, that's 26 letters, 26 options, A, B, C, D, all the way down to Z, okay? Now, digits, how many digits are there? Be careful. Don't forget 0, right? 0 is a digit. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 digits. Can't forget 0. Sometimes students forget that 0 is a digit. There's 10 options, right? 0 to 9. Okay? So if we think about this, what we're doing here is we are choosing 3 letters and 4 digits. Now, again, we're choosing not 1 letter and 1 digit, we're choosing 3 letters. So how many ways are there to choose 1 letter? Well, there's 26, right? We have 26 options. The fundamental counting principle tells us we can just multiply our choices for, each thing we have to do in order to get the total number of different ways it could turn out. So often with these, it's handy to put in a little like you'll see as we go through these, we're often thinking about arranging them or trying to keep track of our choices. So I like to do this. I like to go, okay, we're going to choose 3 letters and then 4 digits. And that just kind of lets us think about how many spots we have to fill, okay? Now, there are allowed to be repeats. So we can have 26 letters to choose from in our first spot, and we still have all 26 to choose from in the second spot, right? So even just the first two letters, there's going to be 26 times 26 options, okay? In the next spot, we still have all 26 options for our letters, right? Again, it doesn't say we can't repeat letters, so it could be, AAA, right? That's fine. Or AAB, or ABB, or BBB, or AAC, right? You can see what I'm talking about, okay? So that's the number of ways we can choose the 3 letters. Then we're going to follow that with 4 digits. So how many ways could we, put a digit here? Well, there's 10 different digits we could choose from. And then there's 10 different digits we could choose from here, and 10 different digits, and 10 different digits. So do you see how this is just the fundamental counting principle in action, right? Again, if there's P ways to do one thing and Q ways to do another thing, there's P times Q ways to do both things. So if there's 26 ways to choose 1 letter, 10 ways to choose 1 digit, there are 26 times 26 times 26 times 10 times 10 times 10 ways to choose 3 letters and then choose 4 digits, okay? So multiplying that out, that's definitely one that you'll probably want to use your calculator for. It ends up being a very big number, but it gives us 175,760,000 unique license plates that could be made before we completely run out, right? That's all the different arrangements of letters and numbers you could make. After that, you're going to have to start, making a new system for making license plates, okay? But we can make that many different ones without repeating any ones that we've already made. That's the number of possible different ways this could turn out. Cool, right? It's a problem that kind of makes your head spin at first, but the fundamental counting principle makes it actually not too hard of a problem to solve. Okay, let's try this one. So a large portion of the written Cree alphabet consists of 9 symbols. This covers a big chunk of the written Cree alphabet. There's more to it than just this. There's some symbols to represent just consonants and one to represent just a vowel. But this covers a lot because, as you can see here, 8 of these symbols represent consonant sounds. So consonants being, not A, E, I, or U. So like P or K, those are consonant sounds. The orientation of the consonant symbol, 4 different orientations, and the boldness of the symbol, whether it's bold or not bold, show which vowel sound the consonant sound will be followed with. Okay, that bold or not bold, sometimes you'll see it as well written with, instead of bolding and not bolding, there's another system where there's like little breaks put into it, little like gaps almost in the symbol instead of using bold or not bold. But the bold or not bold is a pretty commonly used form. Okay, so they show which vowel sound the consonant will be followed with. Let's just look at these examples. Makes it a little easier to follow than trying to read it, right? These systems are often easier to see in action than to try and read about. So what it's saying here is that if you notice this symbol here, right, kind of looks the same except it's rotated differently, okay? Now it tells us that this is the symbol for a P sound. So things starting with P, the P sound, okay? So if it's right side up like this, well, I don't know, I guess right side up is relative, but if it's kind of making this shape here, then it's pe, like in pet, okay? If it's like this, the upside down version of this one, it's pi, like in pick. Like this, it's paw, like in pot. And like this, it's pa, like in pan, okay? Whereas if it's bolded, and right, so same orientation, but now bolded, it's a long E sound, like peak, okay? Same thing, but bolded, it's a long I, like pine. Same thing, but bolded, long O, like pole, okay? And same thing, but bolded, it's long A, like in pay. Okay, so pretty cool, right? Just this different orientation and boldness lets us use one symbol to represent 1, 2, 3, 4, 5, 6, 7, 8 different sounds, right? Unlike in the English written alphabet where we would need to actually write out all of these different combinations with the vowel, we can actually just use one symbol and rotate it and or make it bold to give off the sound we want, right? So if you saw this, it would be said as pa. If you saw this, it would be said as pie. If you saw this, it would be said as pe. Pretty cool, okay? And so there's 8 of these for 8 different consonant sounds. And you can imagine with that and the orientation and the bolding or not bolding, it's a pretty efficient way to actually represent a lot of different sounds. Pretty cool, okay? So there's other symbols, as I mentioned, that are then used for consonants that are not followed by a vowel. So for example, the P that's in lap, right? We're not saying lap-pa or lap-po, we're just saying lap, and we want to end it with just p, right? It's actually just a vertical line, okay? Now, what's it actually asking us to figure out here? How many consonant followed by vowel sounds are possible in the written Cree alphabet? Okay, so let's think about this, right? It told us that 8 of the symbols represent consonant sounds. The orientation of that consonant symbol, and there's 4 different ways we could orient it. So there's 8 symbols that represent different consonants, 4 ways they could be oriented, and then they could be bold or not bold, right? So let's just think about our options here. We've got 8 symbols that could be orientated 4 different ways. Each of those 8 symbols, if we rotate it in 4 different ways, it gives us a different vowel sound. And then on top of that, if we rotate it and bold it or not bold, I'll just say bold / not bold, that gives us a different sound, okay? So that means we've got, well, 8 times 4 times 2 different consonant followed by vowel sounds that we could make, right? 8 different symbols. For each of them, we could orient it 4 different ways, and for each of those, we can make a different sound by making it bold or not bold. So 8 times 4 is 32, times 2 is 64 different sounds, right? Now, obviously, there's more to it than just consonant followed by vowel, because what about just vowel and just consonant? But just for the consonant followed by vowel sound stuff, right? The fact that we have these different options we compare together, right? 8 symbols, 4 orientations, and making it bold or not bold gives us 64 different consonant followed by vowel sounds. Pretty cool. Okay, let's move into a word that I mentioned earlier, but now we will formally define and talk about. That is a permutation. All right, so all a permutation is an arrangement of objects, people, or events. Okay, that's what we call a permutation. So we're talking about like the number of permutations of something. It's just talking about the number of different ways a set of objects could be arranged. Okay, so in a permutation, notice that that word arrange implies that the order is important. So in a permutation, the order of the objects is important. A different order for the same objects is still considered a unique outcome. To show you what I mean, right? For example, ABC, ACB, BAC, BCA, CAB, and CBA. All of those contain the same letters, right? They're all just made up of A, B, and C, but they're all actually considered different outcomes, different, results when we're dealing with permutations, even though they each have the same parts. Order matters, right? If I have, if there's student and teacher, okay, if we're talking permutations, this is considered a different outcome. Teacher on the left, student on the right. And that's what a permutation is. These are two permutations for how many ways there are to arrange a teacher and a student, right? If there's only two things, well, there's two options. You could do student on the left, teacher on the right, or you could do teacher on the left, student on the right, right? And those are permutations. That's two different permutations for how it could be arranged, okay? So let's just think about this a bit, when order matters and when it doesn't. We're mostly in this lesson going to be thinking about permutations where order does matter, but in the next lesson we're going to talk about combinations where order doesn't matter. Okay, so let's get our bearings here. So we began this lesson by looking at the possible outfits you could make by choosing from 2 pants, 2 shoes, and 3 shirts. So what do you think? Does this seem like an example that involves permutations? Does order matter here? Does the order that we choose things matter? I'll give you a second to think about it. Okay. If I wear, let's say I wear khaki pants, yellow shoes, and a red shirt. Is that a different outfit than if I wear a red shirt, yellow shoes, and khaki pants? No, right? I'm still wearing the same outfit. So the order I choose them there doesn't matter, right? No, it wasn't. Order doesn't make a difference. Doesn't give a unique outcome. Order doesn't make a different outcome. Choosing the same things in a different order doesn't result in a different outcome, right? It's the same outfit if the same things are chosen in a different order. Right? Again, just to use that example, if we do khaki pants, yellow shoes, red shirt, so khaki pants, yellow shoes, red shirt, if I put that stuff on, I'm still wearing the same outfit as if I put on my red shirt first, then my khaki pants, then my yellow shoes, right? At the end of the day, it's not a different outcome. I still have the same outfit on, okay? Then we looked at an example where we were talking about different ways to make license plates. Now, what do you think about that? Did that involve permutations? If you choose the same numbers and the same letters, but you put them in a different order, have you made a different license plate or not? Yes, you have, right? Yes. Order matters, right? The same numbers / letters, but in a different order is a different license plate. Is a different license plate. Sorry, that was a bit wordier than I intended. Okay, right? For example, if your license plate is ABC1234, that is a different license plate than ABC even just 1243, right? Or ABC2134 or ABC 4231, right? All of those are different license plates. Not even switching around the order of the letters there, right? Same goes for CBA 1234. So yes, definitely choosing the same things but just arranging them differently is a different outcome. It's a unique thing. So in this case, in the case of license plates, that would be a permutation. Okay, the order matters. Same thing, but in a different order is considered a different outcome. Okay, now I'm going to introduce something new to you, something called a factorial. Okay, be careful. It's not the same thing as a factor. It's a factorial. Okay, it might seem a little random at first, but they are going to pop up a lot when we're thinking about this stuff. And that's why we're going to introduce them here first, and then we'll see why they kind of naturally show up whenever we're thinking about the number of different ways to arrange objects. Okay, so factorials, for what is it? For any positive integer, okay, the factorial of that integer is nothing more than the product of all positive integers that are less than or equal to that integer. That's a lot of, terminology for something that's actually a very straightforward idea, but important to get that proper definition down first, okay? How do we indicate a factorial? We use an exclamation mark. So I remember when I first learned about factorials, I felt like the math was yelling at me, okay? But for example, we would say this out loud as 4 factorial, okay? And all it means, 4 factorial, it's the product of all integers less than or equal to 4. That's 4 factorial. So what integers are less than or equal to 4? Well, 4 is equal, and then 3, 2, and 1 are less than it, right? So 4 factorial, it's just 4 times 3 times 2 times 1, right? That's 4 factorial. Start at 4, multiply every integer down to 1. We would read it out loud as 4 factorial, okay? 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? 100 factorial would be 100 times 99 times 98 times 97 times 96 times 95, all the way down to 1. And that's it. We multiply them all together. That's a factorial. Now, what does this have to do with permutations? Well, I think the best way to kind of see why factorials just kind of naturally pop out when dealing with probabilities and the number of different possible outcomes, I think the best way to see why factorials show up here is honestly just to look through it with an example here. So let's say there's a race happening and there's 5 people in the race. Just to keep things simple, we're going to give the racers very simple names. We're going to name our racers A, B, C, D, and E. Okay, so we've got 5 different racers. One's named A, one's named B, C, D, and one's named E. Okay, what it's going to ask us here that we're going to think through is how many possible different outcomes could there be for how the race is finished. So when you look at, the results for the race, how many different possible ways could it turn out? We want to know, right? How many ways are there for someone to come in first, second, third, fourth, and fifth? So order definitely matters here, right? Because it's the same 5 people. We're just interested in how many different ways could those 5 people be arranged, essentially, right? A could be in first, or B could be in first, or C could be in first, and D could be in first, and E could be in first, right? And then for all those options, who's in second? Well, it could be B, C, D, or E. Who's in third? Could be C, D, or E, right? All of those different arrangements. So we could look at it this way. I labeled a few possible outcome branches on this. I didn't label all of them because you can probably tell it would be a nightmare to look at, okay? You can also see why tree diagrams are great, but they have limited practicality, right? I mean, this isn't even that crazy of a situation. It's just 5 people in a race, and already our tree diagram is pretty humongous looking, okay? So here's the idea, right? You could have A in first, and then you could have A in first, B in second, or A in first, C in second, or A in first, D in second, or A in first, E in second. right? And then for each of those, for A in first, B in second, for example, you could have C in third, you could have D in third, or you could have E in third. And then for each of those, you could have, D in fourth and E E in last, or E in fourth and D in last, right? Or C in fourth and E in last, or E in fourth and C in last, right? That's what we're mapping out here. So here's one possible outcome if you just watch, along this branch here. That's one possible way it could turn out. That represents A, then B, then C, then D, then E. But even just switching around D and E, that's this outcome, right? Now imagine doing that for every possible arrangement, okay? And you can do all of these different outcomes, all of this, right? All of this whole branch of our tree here, all that represents is A coming in first. Then we have to think about all the different ways it could turn out if B came in first. Then all the different ways if C came in first, then D, then E, right? And so that's what our tree diagram is trying to show us here. But here is where factorials pop up, okay? Think about it this way. If we are placing the racers, we're trying to say how many different ways could they place, right? Well, if we've got our 5 racers, we can say there are 5 different people who could finish in first place, right? 5 different options for who comes in first. So we take one of them, we put them in first place, right? Choose one of our 5 and put them in first place. That leaves us with 4 options left for who could finish in second place, because for each of those 5 people, right, well, we've already put them in first place. So there's 5 different ways we could have a first place finisher. For each of those 5 different ways, there are 4 people left who could finish in second place, right? For each of those first and second combinations, there's now 3 people left who could finish in third place, right? There's already 2 people in the first and second for each of these outcomes. For each of those first, second, third combinations, we have 2 people left to finish in fourth place, right? We've already got someone in first, second, and third for each outcome. And then for each of those first, second, third, fourth, there's only 1 person left, right? We've put someone in first, someone in second, someone in third, and someone in fourth. So there's only 1 person left to finish in fifth place, right? And that's what we're saying here. There's 5 different people we could put in first. For each of those, there's 4 different people we could put in second, right? 4 different people, 4 different people. 4 different people in second, 4 different people in second. For each of those, there's 3 different people who could go in third who are left, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. And then for each of those, there's only 2 people left to put in fourth place, right? So 2 different outcomes still, okay? But 2 options there. D in fourth and E in fifth versus E in fourth and D in fifth is a different outcome. And so if we think about that and apply the fundamental counting principle, right, there's 5 ways to choose first place, leaving us with 4 people to choose for second place, 3rd for third place, 2 for fourth place, and only 1 for fifth place. Well, the fundamental counting principle tells us multiply all the number of ways there are to do all of the things together, and that gives you the total number of ways the overall situation could turn out. So it's 5 times 4 times 3 times 2 times 1, which is just 5 factorial, right? And this is why factorials show up whenever we're talking about the number of ways to arrange things, right? If I have, 3 objects, let's say a square, a triangle, and a circle, and I want to know how many different ways could I arrange them, right? Well, think of it this way. I have 3 objects to put in the left spot, leaving me with 2 to choose from for the middle spot, leaving me with only 1 to choose from in the last spot, right? So there's 3 ways to put something in the first spot, 2 ways to put something in the next spot, and leaving me with only 1 choice to put in the last spot, right? So the total number of ways this could go is 3 times 2 times 1, or 3 factorial, which is 6, okay? So naturally, if we have n objects, there are n factorial ways to arrange n objects. Okay, so the total number of possible outcomes for this race, for who comes in first to fifth, would just be 5 factorial. 5 racers, so there's going to be 5 factorial, 5 times 4 times 3 times 2 times 1 ways to arrange them. Okay. Now, sometimes we're not interested in arranging all of the possible options. We just want to arrange a certain selection from a larger group, which means sometimes we don't always want to use the entire factorial. Okay, we might only need to think about a certain selection from a larger group. So let's continue using our race example here to think about it. So for example, suppose that in the same race, they were giving out a gold, a silver, and a bronze medal to whoever comes in first, second, and third place, respectively. Okay, then it asks us how many possible ways could the gold, silver, and bronze medal be awarded. So notice here, we now don't really care. Which 2 places don't we really care about? We don't really care about 4th and 5th, right? If we're just interested in how many different ways can gold, silver, and bronze be awarded, is this a different outcome in that context than this, right? If we look at it this way, A got gold, B got silver, C got bronze. If we look at it this way, A got gold, B got silver, C got bronze, right? So now we don't actually care about what order the 4th and 5th place came in, because that doesn't make a difference to what we're interested in. What we're interested in is how many ways are there to award gold, silver, bronze. And the order of the 2 people who didn't get that medal, didn't get any medal, don't change that outcome, right? So looking at that here, there are 5 different people who could win gold. 4 different people remain who could win silver, because in each outcome, 1 person has already been assigned gold, right? And in each outcome, now there are 3 different people remaining who could win bronze, because in each outcome, 2 people are already assigned with gold and silver, right? And then again, we don't care about who came in 4th and 5th. So all we're saying now is, okay, if A comes in first, there's 4 people who could win the silver. And then for each of those 4 people who won the silver, 3 people are left who could win the bronze, right? Or B could win gold. For that outcome, there's 4 people who could win silver. And for each of those 4 people who could win silver, there will be 3 people left who could win bronze, right? So using the fundamental counting principle, there's going to be 5 times 4 times 3, which is 60 different outcomes for how gold, silver, and bronze could be awarded. So you can kind of see this is sort of like 5 times 4 times 3 times 2 times 1, right? It's sort of like 5 factorial, but it's leaving out the 2 times 1, right? It's like 5 factorial if we took off the 2 times 1 part, right? And again, that's because of what we talked about. 4th and 5th place have no effect on the winners of gold, silver, and bronze. And we were trying to figure out how many different ways are there for gold, silver, and bronze to be awarded. If racers A, B, C win the medals, it doesn't matter if 4th and 5th place goes to D and E or to E and D. Okay, since we're only interested in 3 selections here, gold, silver, bronze, the order of the remaining 2 is not relevant to the total number of outcomes in this context. So notice we used to have 120 different outcomes when we worried about how many different ways are there for all 5 to finish, right? And now we're left with 60 outcomes because none of these count as different outcomes if all we're worried about is who got gold, silver, and bronze, right? And you'll notice here, if this is 120, right, and there's kind of 2 finishes there, what are we left with? Well, 60 in the previous set of branches, okay? 5 times 4 times 3, okay? So this logic here kind of explains what this formula is that we're about to talk about and this notation. So we've got here NPR notation. We sometimes say, like out loud, we'll say NPIC R. The P is really for permutation, or NPermute R, okay? So when dealing with permutations, we often represent it this way. Okay, what is the N? What is the R? Okay, N is just the total number of objects there are to choose from. It's your options. How many different options do you have to choose from? R is the number of objects that you'll actually choose. So just going back to our race example, right? At first, we were choosing all 5. So we could have written that as we had 5 options. We're picking all 5. So we would have written 5P5, right? Later, we were just doing gold, silver, bronze. So we would have done 5, but we're not choosing all 5 of them. We just want to pick 3. So we would do 5, pick 3, okay? N is the options, R is how many you're actually going to pick, okay? The P is, you'll never put in a number for P. It's just written to say that we're talking about the number of permutations to choose R things from N options. So for example, 5P3 would be a perfectly valid way to write that, okay? So what NPR does, NPR tells us the number of possible ways to choose R things from a group of N options when order matters. We will see another similar thing in the next lesson. We'll look at NCR, that's for combinations instead of permutations. We'll use those when order doesn't matter. So I'm just going to run you through the steps because NPR is something your calculator can do, okay? First, I'll run you through the steps, and then we will go to our calculator to confirm our answer, okay, to the previous 2 examples. So what we're going to do is we're going to first enter N. That's the number of things there are to choose from, okay? You have to do that first. Some of the newer calculators, it's okay if you don't do this first. You can go back and enter it later. I know like on my calculator, it's a TI-83. I have to enter the N first. So if I want to do 5, pick 3, the first thing I actually have to press is 5, okay? Then you're going to press math. And at the top, you're going to move right to PRB or prob. Both mean the same thing, just different calculators write it in a different way, okay? You're going to press 2 for NPR. You'll see that when we do it here. Finally, enter R, the number of things that will be chosen, and press enter. And it will just calculate that for you. It'll tell you how many ways are there to choose R things from N options if order matters. Okay, so let's just go back to our race example and try this out, see what our calculator can tell us. So first we had 5 people to choose from, and we had to choose all 5, right? We had to assign each person a placement in the race. How many ways are there to arrange 5 things chosen from 5 options? So we had to determine the value of 5 permute 5, or 5 pick 5, we sometimes say. Let's use our calculator to confirm our previous answer of 120. So here we go. Okay, so first, I want to do 5 permute 5, or 5 pick 5. So I'm going to say 5, and then we're going to go to math, right below second and alpha. Okay, math, and then you see on the top there, prob. Older calculators, like my usual calculator, will say PRB instead of PROB, means the same thing. And then do you see option 2 there, NPR? That's what we want. So I'm going to say option 2. And so now it's doing 5 permute. Yours might not quite look like this. I know mine doesn't make the 5 go down like that. It'll just be 5, and then it'll say NPR. And now I want to do 5 permute 5, so I'll just put a 5 in there. Okay, yours might look slightly different. Mine actually, my main calculator actually does. This is just the online calculator that actually puts the 5 down like that. Okay, but then we'll hit enter, and look at that, 120. Okay, so it worked. Looking at the next one here, then we had 5 people to choose from, and we had to choose 3 of them. So 5 options, but we're only actually arranging 3 chosen from those 5 options. That was when we were assigning 3 people out of 5, gold, silver, and bronze. So what were we doing? We were determining the value of 5 pick 3, right? How many ways are there to arrange 3 things chosen from 5 options? Let's see if we can use our calculator to confirm our previous answer of 60. So now I want to do 5, and I'll go math over to probability. Option 2, I want permutation, so 5 permute 3. And it gives me 60. Okay, so going back to here, we got it, right? We confirmed our previous answer of 60. Okay, now, again, honestly, especially for these permutation ones, the formula or the symbol here in the calculator honestly aren't aren't going to help you too much. I mean, I shouldn't say that. They are helpful, but personally, I find it a lot easier to actually just think about it, right? Think about the different arrangements, especially when things get more complicated and we have like restrictions or certain conditions that we have to meet. It's often easier to just kind of map it out and think about, okay, I have this many options for this, and then that many options for that, and then that many options for that, and multiply it out yourself, okay? But I want to just make sense of what NPR is actually doing, because it's locked behind the mystery of our calculator. We put it in, calculator spits out a number. What's actually happening? Well, what's happening is it's just using the formula that is on your formula sheet. And again, we'll explain why this formula makes a lot of sense. Okay, so here it is. If you check your formula sheet, you will see this formula, that NPR is just taking n factorial and dividing it by n minus r factorial. Okay, now why would it be doing this? Well, again, I think having a concrete example helps think about it. Okay, so let's think about it in terms of our race question. When we were only choosing 3, right, when we were assigning gold, silver, and bronze, we wanted to do 5 times 4 times 3, because there's 5 people who could finish first. For each of those, there's 4 left to finish second. And for each of those, there's still 3 people left to finish third, right? So 5 times 4 times 3. And we can kind of think about that as 5 factorial, except leaving out 2 times 1, right? Since n is 5 and r is 3 in the example, the formula above becomes, if we put in 5 as our n, okay, and 3 as our r, we get 5 factorial over 5 minus 3 factorial, okay? What is this actually doing here? Well, by doing n minus r, what are we figuring out, right? We're choosing 3 things. So if we do 5 minus the things that are chosen, right? Take our total options and subtract the number of ones we did choose. What are we left with? We're left with the number of things that were not chosen, right? Take all of the options, subtract off the number of things that were chosen, and you're left with the number of things that were not chosen. And do we care about the order of the things that are not being selected? No, we don't. Right? So there's 5 factorial ways to arrange 5 things, but we're not arranging all 5 of them, right? We're only choosing 3 of them to actually arrange. And so we don't care about how many ways there are to arrange the 2 things that are not being chosen. That's exactly what we said before, right? We don't care about who comes in 4th and who comes in 5th. If we switch those around, it doesn't actually give us a different outcome. So what this right here represents, this n minus r, which in this example gave us 2, right? That's the number of ways to arrange the things that were not selected. Right? The order of 4th and 5th, if it's D then E or E then D or A then B or B then A, doesn't matter in the context of how many ways are there for someone to win gold, silver, bronze, right? And in general, that's what this formula is doing. How many ways are there to arrange R things chosen from a group of n options? Well, there's n factorial ways to arrange n things, but we want to divide out the number of ways there are to arrange the things that we're not actually going to be choosing, right? And so that's exactly what we see happening here. 5 times 4 times 3 times 2 times 1 divided by 2 factorial. There's 2 factorial ways to arrange 2 things, so divide by 2, divide by 1. Look at that. It gives us what we kind of intuitively wanted to get, right? 5 people who could finish in first, 4 for each of those to be in second, 3 left for each of those to be in third. 5 times 4 times 3. We don't care about the 2 factorial part, and this formula divides it out for us. So hopefully we can kind of see why this formula makes sense, right? We wanted to know how many ways there were to arrange 3 things, chosen from 5 options. Since we're only choosing 3 things, the ordering of the 2 things which aren't chosen don't matter. So we need to exclude those outcomes when counting the total unique outcomes. n factorial represents the total possible ways to arrange n things. If we choose r things from n options, then n minus r is the number of things that aren't chosen, right? If we choose three things out of 5 options, that means we didn't choose 2 of them, and therefore we don't care about their order, right? And therefore, n minus r factorial, that's the number of ways to arrange the things that aren't chosen. Since these arrangements don't actually give us unique outcomes for what is chosen, because they weren't chosen, we divide the n factorial by them to cancel them out. And that's the logic behind this formula. So yes, you're given this formula, but we can actually see that it's just applying the concepts we've been talking about. Okay. Quick note on how to enter a factorial. Sometimes that's something we might want to enter. Okay. We talked about doing NPR. To enter a factorial, okay, you're actually going to go to the same place. Basically, the calculator steps for this unit are all located in the same place. That's going to be in math, and then scrolled over to prob or perb. Okay. And then you'll see option 4 is a little exclamation mark. That's your factorial, right? And press enter. So just to show you one, how about 10 factorial? Actually, let's do 5 factorial because we found that that was 120, so we can check our work here. So I'm going to go 5. I'm going to press math, go over to prob. Okay, and then do you see option 4 there? It's a little exclamation mark. So option 4, 5 factorial is, we got 120 before. Let's see. Sure enough, 120, right? Of course, you could also just do 5 times 4 times 3 times 2 times 1. Okay, 120. That can be a bit annoying, though, when you're dealing with something like 20 factorial or 15 factorial. Okay, let's try out some examples here. So, 7 friends go to the movies. If they all sit next to each other in a row, how many different ways could they be arranged? Okay, so there's 7 options. How many of them are we actually picking? Yeah, all 7, right? They all sit next to each other in a row. So our n is 7, and they're all sitting next to each other, so we're choosing all 7 of them. Okay, now personally, I would just actually approach this like this, right? It's 7 factorial, right? One way to look at it, 7 spots, 1, 2, 3, 4, 5, 6, 7. We know they're all sitting next to each other in a row, so there's no like gaps or anything. Well, think of it this way. You've got 7 people, meaning, 7 to choose from there, leaving you with 6 people who could go in the next spot. For each of those, there's 5 people left to put in the 3rd spot, then 4 people left for each of those. For each of those, there's 3 people left, then 2, then 1, right? So fundamental counting principle. It's just 7 factorial, right? And 7 factorial gives us 5,040 different arrangements. Okay, 5,040 different arrangements. Okay, could you use the formula? Sure. If you go into your calculator and go 7p7, it will tell you 5,040. But personally, especially when things get a little trickier with these, when there's conditions and stuff, that's not telling me much, right? That's not helping me understand what's really going on here. And if there were restrictions here, it's definitely not helping me deal with those, okay? You could also, we could confirm with the formula that 7 permute 7 is n factorial. So here, I'll just write it up here. NPR is n factorial over n minus r factorial, okay? So looking here, our n is 7 factorial, over 7 minus 7 factorial, right? Which gives us 7 factorial over, now 7 minus 7 is 0 factorial. We're going to talk about this. You might think, we're dividing by 0. This is going to seem weird, but 0 factorial actually equals 1. Okay, I know that seems odd, but here's the idea behind it, right? Remember, factorials are saying how many ways are there to arrange this many objects. If you have 0 objects, there's only one arrangement, right? It's just, there's nothing. You can't rearrange nothing. So there's one arrangement, but that arrangement is just having nothing. So 0 factorial is just 1 because of that fact. Okay, so 7 factorial over 0 factorial is actually just 7 factorial over 1, or 7 factorial, which is 5,040. Okay, Let's try this one out. A principal wants to take a photo of 6 teachers in front of the school. 10 teachers volunteered as willing to be in the photo. How many different ways can the principal arrange 6 teachers in the photo? So be careful. This is not just 10 factorial, right? Because we're not putting all 10 teachers in the photo, okay? It's also not just 6 factorial because we have more than 6 options, right? Again, I find the easiest way to think about these, we've got 6 spots, 1, 2, 3, 4, 5, 6, right? We got to fill all 6 of them. So I could put 10 teachers in this spot. That leaves me with 9 teachers I could put in that spot. Then I'm left with 8 options, 7 options, 6 options, and 5 options. So you can see why this isn't just 6 factorial, right? Because we actually have, it's not just 6 options and we're left with 1. We could put different teachers in each of these spots, leaving us with, even by the time we get to the end, we've still got 5 different teachers we could put there, right? So 10 times 9 times 8 times 7 times 6 times 5 gives me 151,200 different possible ways, right? And again, because we're only choosing 6, some of those different ways are the same teachers but in a different order. And some of those different ways are with different teachers altogether because we are choosing 6 from 10 options, right? So some of those outcomes might involve just different teachers being chosen in the first place, and a lot of them involve the same 6 teachers but arranged in different ways, right? And there's 151,200 ways to pick your 6 teachers and to arrange the 6 teachers that you've chosen, right? Kind of a mind-boggling calculation when you think about it that comes down to something pretty simple thanks to the fundamental counting principle. Another way we could have approached this, let's think about it. How many options are there? What's n? N is 10, right? And how many are we choosing? 6. So R is 6, okay? So N is 10, R is 6. So we could have approached this as 10 permute 6, which according to the formula, we would say 10 factorial, right? Let's think about what this is saying. There would be 10 factorial ways to arrange 10 teachers, but we don't care about the ways to arrange 4 factorial because no matter which outcome we look at, we're not actually arranging 4 teachers, right? Because we're only choosing 6. So that's why we do n minus r, 10 minus 6 factorial, right? Because the 4 teachers who aren't chosen, it doesn't matter how they're arranged, they're not in the picture. So this gives us 10 factorial over 4 factorial. The number of ways to arrange the 4 teachers who are not chosen needs to be divided out here. And that gives us 3628800. That's 10 factorial. Over 4 factorial is 24, right? 4 times 3 is 6, 4 times 3 is 12, times 2 is 24, times 1 is still 24. And guess what? It gives us the same result, 151,200 different possible arrangements of 6 teachers chosen from a group of 10. Okay, cool, right? All right, so here is one from a released diploma, okay? It's a written response question, so we're going to talk a little bit about this one, but let's just first read the question. A student is asked to encode the word factor by replacing each letter of the word with a different math symbol. There are 10 math symbols available. The student creates a key, a list of his letter symbol replacements, and gives it to his partner to use to decode the word. Explain how you would determine the number of different keys that can be created for the word factor and determine the number of possible keys using your strategy. Okay, so this term here, this bolded directing word, explain, that is important. That means something, okay? So this has all been shared with you, or at least it will be soon as we get closer to the diploma, okay? This is the list of terms. This comes straight from Alberta Education, okay? So they don't just kind of choose their words, willy-nilly. Every word they use has a connected meaning. So when they say explain, they are wanting an explanation. I can tell you right now, if you say this, if this is your answer to this question, which is the right answer, by the way, and it's even the right like math we're going to do, at best, and I don't even know for sure if you would get this, you would get 1 out of 2 at best. Because what have you explained, right? You haven't explained anything. You've written down some symbols. Okay, look here. Look at the definition of explain. I mean, I'm sure we know what explain means, but make clear what is not immediately obvious or entirely known, right? If you looked at that, pretend you weren't a Math 30 student, and I showed you that, would you say, oh, yes, you've definitely made clear what was not immediately obvious, right? When you're solving these, especially these explain ones, a good way to think about it is like you are teaching someone how to solve the problem, right? You're explaining it to someone. The diploma markers, they're not allowed to fill in the gaps, right? They're not allowed to assume that you understood. Everything that you want marks for, you need to show, right? They have to, I often say for written response questions, it's not really about what you know, it's about what you show, right? You have to show them, make it obvious that you do understand what you're doing and why you're doing that, right? This is not an explanation. This has not made clear what was not immediately obvious, okay? So what I wanted to do here was take a look at a couple of examples of solutions to this question. These are real solutions put forth by students and the marks that they got. And I want to look at where they lost some marks, okay? So it's the same question. So it asks us, explain how you would determine, right? We just looked at the question. So this student said they're going to put 6 lines to represent each letter. Okay, they're going to write 10, 9, 8, 7, 6, 5 in each spot. Well, why, right? Why 10, 9, 8, 7, 6, 5? They're right. That is actually, they got the right answer. Look at their mark. They got 1 out of 2, right? They even do have some explaining. But why are we doing 10, 9, 8, 7, 6, 5? How does that relate back to this, right? Well, look here. Even though the explanation describes the mechanics of finding the number of keys, the student does not link order and non-repetition to the numbers used in the calculation, right? That's what was standing between a 1 out of 2 and a 2 out of 2 for this student. They're right. We should do 10 times 9 times 8 times 7 times 6 times 5. But why should we do that? Well, because we can't repeat the symbols. Otherwise, our code won't really work, right? If we use the same symbol for F as we do for A, how is someone supposed to decipher our code, right? And so that's the simple thing they were missing, but it's an important thing, right? That has not made clear what was not immediately obvious, right? Again, if you had never taken Math 30, would you be able to say, oh, I get why they did that? Not with this explanation, really, right? They've even said it represents how many symbols they can choose, but why is it 10 times 9 times 8 times 7 times 6 times 5 and not 10 times 10 times 10 times 10 times 10 times 10? Well, because we can't repeat symbols, right? That was important, okay? Multiply them all together. That is how many possible keys there can be. And that's right, but why do we multiply them together? Using some proper math terminology, right? The difference between a 1 out of 2 and a 1.5 out of 2 might have just been here saying because of the fundamental counting principle, right? That shows that fundamental counting principle is something you can draw on to justify your answer. That's a well-known, properly defined, properly cited math principle there that you could pull up, right? By the fundamental counting theorem. We can multiply it like this, okay? This is the correct answer, okay? It is, but they only got, well, 50% on this question. And it's not because they did anything wrong, it's because they didn't explain, and the question asked them to explain. So they got 1 out of 2 because they got the right answer, but they didn't actually do what the question asked, which was explain, okay? Let's look at this one. They got 1.5 here. Again, same thing. The explanation does not explicitly address the fact that symbols cannot be repeated, right? Again, think of this like, how would you teach this to somebody, right? Now, you don't have to teach them like grade 7 math or anything, but imagine teaching like a Math 20-1 student, right? Someone who's about to start Math 30-1. How would you explain to them why we're going to do what we are doing? Right now, again, look, they got the right answer. They used a slightly different method. They used another way you can approach this, which won't make much sense until we do the next lesson where we talk about combinations. But we can still take a look at what they were missing here, right? They said there are six permute six different ways in which you can represent a letter for each of the six, but all they left out was that you can't repeat the letters, right? And that is important. They're right. This is what we need to do, but they're missing a little explanation before this saying why we can't repeat them, right? Why is it not 10 times 10 times 10 times 10 times 10? Why is it 6 permute 6 instead, right? We're not allowed to reuse them, okay? This one here also got 1.5 here. It says it includes a partial explanation. Let's see, can we pick out what they are missing in their explanation? Once again, they have the right answer, okay? But it says there are 6 letters in the word factor, and for each letter there is 10 math symbols. Therefore, to get the number of, what's that say? Keys, I will start with 10 choices multiplied by 1 less each time. That's great, but why, right? Oh, because one math symbol cannot be 2 letters. Okay, that's a pretty good explanation. This will stop after 6 letters are completed. Now, honestly, I think all they're missing here is why are we using a permutation, right? Well, order matters, okay? Right? I think that's all that's actually standing between a 1.5 and a 2 here, right? Think of it this way. Every time you kind of make a decision, which we've made a decision here, we used permutations as opposed to combinations. I know we haven't talked about combinations much in this lesson, okay? But by the time you're writing the diploma, when you look at this, you'll have to make a decision. Permutations or combinations, right? And you're making a decision, so explain why you chose one over the other. Doesn't need to be an essay, right? But a quick thing about, okay, the order matters. If I take the symbols and I arrange them in a different order, my code is now different. Let's just take a look at one that got full marks, one that got 2 out of 2 on the diploma. Okay, so it says the response includes a full explanation, which addresses the requirement to select and arrange 6 unique math symbols, and it has the correct number. So notice all of these actually had the correct number. It was the explanation that was missing for some of them, or at least not complete. Okay, so look at the things they say. There's 10 math symbols to choose from. There are 6 letters in the word factor. So we need to choose 6 symbols, okay? Now, this part's going to go into a slightly different strategy than what we know how to do. We can solve this with just the stuff we've learned in this lesson, but I'm more focused here on how they're explaining themselves. So don't get too bogged down in the fact that they're talking about combinations here, okay? Focus on how they're explaining themselves. So they talk about, right, at this point, I'm only choosing 6 symbols from 10, and the order they're chosen doesn't matter yet, right? So look, they're explaining. Why are they not considering order? Now look, after choosing the letters, I need to arrange them. I need to arrange them to each represent a letter in the word factor. Because each letter is unique, the order I arrange the symbols now matters, right? That's really all this one was missing, right? I will arrange the 6 symbols so one matches a unique letter. To find the possible arrangement for 6 items, we can do 6 permute 6. Okay, because we need to choose and arrange, we multiply, yada, yada. But see what I mean? They're not doing any different math than these people. They're just explaining themselves, right? They did exactly what this student did mathematically, but they explained why they did what they did. Okay, so that key word there, explain, is very important. So with that in mind, let's try this one out, hoping to get 2 out of 2 on the diploma. Okay, so again, first thing here, right, that I'm thinking, well, there's 10 math symbols available, so there's 10 options for each letter in factor. Let's just write that. 10 symbols available. And now I'm about to talk about the fact that I'm going to use a permutation, right? And again, we might not have talked about combinations yet, but that is a decision we are making, okay? By the time you write the diploma, though, you'll have both of those tools in your kit. So if you decide on permutations, if you decide order matters, explain that, right? It just takes a quick sentence, a quick bullet point. Order does matter, right? A different, the code is different if the same symbols are arranged in a different order, right? Like if I make F, I don't know, pound, or if I make F star, right? If I go, like pound, star, exclamation, slash, tilde, what's another symbol? $sign, right? Even if I use all those same symbols, but a different order, I've got a different code now, right? If my code is instead $sign, exclamation, star, tilde, slash, hashtag, or I shouldn't call it a hashtag, a pound or an octothorpe, right? That's a different code, even though it's all the same symbols. So order matters, right? We should say that. The code is different if assigned symbols are rearranged. Now I've explained why I'm going to use a permutation instead of a combination. Okay, so we can use permutations. So I'm going to reference, so could use permutations and apply the fundamental counting principle. And now I'm just going to address the fact that, again, like when you go to do it, right, if you start writing something like 10 times 9, take a second and reflect and ask yourself, have I explained why I'm doing 10 times 9 times 8, right? Have I explained why I'm doing that? And I haven't, have I? Right. I haven't said that the reason I'm going 10 times 9 is because we can't repeat symbols. So once I use one here, that's no longer an option to use here, because if I repeat symbols, then one symbol could represent 2 letters, meaning it's not a very helpful code, right? One symbol should represent 1 letter for the code to be decipherable. So I'll say letters, or symbols rather, right? Symbols cannot be repeated. Otherwise, one symbol could represent multiple letters. So how am I going to, what does that mean for my math? I can now say, so once each letter is assigned a symbol, there is one less symbol for the next letter, right? Could even say, e.g., 10 options for F, 9 for A, 8 for C, etc. Okay, and the last thing I would say here is another decision I'm going to make is that I'm going to put, right, I'm going to put 6 things here. Why 6? Well, because we're choosing 6 symbols from 10 options, right? I have to code 6 letters. So the last thing I'd say here to explain myself, I'm going to use the fundamental counting principle to therefore assign non-repeating symbols to 6 letters chosen from 10 symbols, right? And now I can go ahead and say we'd have 10 options for the first letter, 9 for the second, 8 for the third, 7 for the fourth, 6 for the fifth, and 5 for the 6th and final letter that we need to encode, okay? And therefore, we would get 151,200, okay? And a little sentence here to explain, what that answer actually means never hurts either. So we could say there are 151,200 possible different keys the student could make. Right? There we go. Okay. Now we've explained everything we did, right? Again, this at best would get you 1 out of 2. Okay. At best. Okay. And it's not because you did anything wrong. It's because you ignored this, right? So again, if you're writing that, you probably know why you're doing it. So ask yourself, okay, why am I doing this? Have I said that, right? 10 symbols available, so 10 options to represent each letter and factor. The order does matter. That's why we're using a permutation and not a combination, right? Why does the order matter? The code is different if assigned symbols are rearranged. So use permutations, apply fundamental counting principle, right? Symbols cannot be repeated, otherwise one symbol could represent multiple letters. There we go. We've covered now why it's going 10, 9, 8, 7, 6 instead of just 10, 10, 10, 10, right? Once each letter is assigned a symbol, there is one less symbol for the next letter. And then just saying, okay, so we need to assign 6 symbols from 10 total options, giving us this calculation. Okay, alrighty, go ahead and try these ones out. Don't need to explain yourself that much for these ones, although if you want practice with the idea of explaining, not a bad idea maybe to try it out on these ones, okay? And there's lots of other examples you can take at this time as well to get a little comfortable with the permutations and the fundamental counting principle. But yeah, so take some time, at least try these out, take a little break from my voice, do some practice, and then when you're feeling good, come on back and we will move on to looking at how we can work mathematically and algebraically with factorials. All right, so it came up in one of those examples, but we're going to start out this section here with just explaining this a little bit more, a special note, and that is that 0 factorial, as strange as it might seem, it's equal to 1, okay? 0 factorial is not 0, it's 1. I know that seems weird at first, but not when you remember that n factorial is really telling us how many ways there are to arrange n things, right? There are 3 factorial, 3 times 2 times 1, ways to arrange 3 things. There are 10 factorial ways to arrange 10 things. So 0 factorial is like saying, how many different ways are there to arrange 0 things, right? Well, there's only really one way. If you have nothing, that's the arrangement. There's nothing to switch around. It still counts as an arrangement, right? It's nothing, but there's no different arrangements of 0 things. There's just the one. It's nothing, right? That you only have you have nothing, and that's the arrangement. There's nothing to switch around. That's kind of the intuitive explanation. We can also kind of look at this idea here. A lot of math and like coming up with these relationships is looking at patterns, okay? So if we look here, 4 factorial is 4 times 3 times 2 times 1. Right? 3 factorial is 3 times 2 times 1. But one way to think of that, 3 factorial, is you could think of it like, well, it's 4 factorial divided by 4, right? Because 4 factorial is 4 times 3 times 2 times 1. If we divide out the 4, we're left with just 3 factorial, right? Just to show you what I mean. 4 times 3 times 2 times 1 over 4 leaves us with 3 times 2 times 1, which is 3 factorial, okay? Similar logic here. 2 factorial is 2 times 1, but you could think of that as 3 factorial over 3, right? That's 2 factorial. 3 times 2 times 1 divided by 3 is just 2 times 1, or 2 factorial. 1 factorial, we could think of it as 2 factorial, but divide out the 2. So continuing this pattern, you can see what we're doing, right? To get to the previous factorial, we take that factorial and divide it by the number that we're factorialing, right? 4 factorial over 4 gives us 3 factorial. 3 factorial over 3 gives us 2 factorial. 2 factorial over 2 gives us 1 factorial. So continuing this pattern, what would 0 factorial be? Well, it would be 1 factorial over 1. And 1 factorial is just 1, so we have 1 over 1, which is 1. Okay, and so that is, kind of a mathematical logic behind why 0 factorial is 1. Okay, so when we're working with factorials, I'll be honest, most of the time it comes down to doing this same kind of step here. Okay, and that step is taking advantage of the fact that larger factorials contain all smaller factorials within them, so to speak. So for example, 7 factorial contains 4 factorial, right? Because what is 7 factorial? Well, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. And what is 4 times 3 times 2 times 1? Well, that's just 4 factorial, right? So really, you could think of 7 factorial as 7 times 6 times 5 times 4 factorial, because 4 factorial is just 4 times 3 times 2 times 1, right? And this fact can often help us simplify these factorial expressions like we're looking at in some of these examples quite a bit. Because, for example, like looking ahead a bit, right? 100 factorial is being divided by 98 factorial. But 100 factorial contains 98 factorial. So if we kind of, expand this out a little bit to think about it, we might be able to cancel 98 factorial out, right? We might have a 98 factorial over a 98 factorial and some other stuff going on. But that's, whenever dealing with factorials and needing to algebraically analyze them, that is often the step that we need to take, at least at some point in our simplification or solution, okay? So it's therefore generally a good strategy to partially expand the factorials up to the point where you can cancel another factorial that it contains. Let's see what that looks like in action with a few examples here. So, first one. 100 factorial over 98 factorial, okay? Well, again, 98 factorial is within 100 factorial, right? So looking at these, it's a good idea to say, okay, which one's larger? And then start expanding that until you get to the point where you can cancel out the smaller one. So what I mean by that is 100 factorial is, well, it's 100 times 98 times 90, well, sorry, I guess sorry, I messed that up right off the bat. 100 factorial is not 100 times 98, it's 100 times 99 times 98 times 97, yes, times 96 times 95, but I'm going to stop there because 98 times 97 times 96 times 95, well, that's just 98 factorial, right? And I'm choosing to stop there because of the fact that we're dividing this by 98 factorial. So this is 100 factorial, but I've rewritten it as 100 times 99 times 98 factorial. Okay, so if I divide that by 98 factorial is just a number. It's a very large number, but it is a number. So 98 factorial over itself is just 1, meaning that this is just 100 times 99. Which is 9,900, right? And there we go. We partially expanded the 100 factorial until we got to the 98 part of it. Because after that, it's just 98 factorial, right? And then we can cancel it out with the 98 factorial that's in the denominator. Let's try a similar one here. Help me out. Which one should I start expanding in order to cancel out? Right, I should start expanding the 11 factorial because I know that 11 factorial contains 10 factorial, right? So this could be 10 factorial over 11 factorial, but that's just 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? But that's just 11 times 10 factorial. That's one way to look at it. And if I stop there, I'll notice, okay, well, 10 factorial over 10 factorial is just 1. So I'm left with just 1 and 11 in my denominator. So 1 over 11. And there we go. We've simplified that factorial. All right, here's an interesting one. We've got 6 factorial over 5 factorial times 3 factorial. Now we've got options here because 6 contains the 5 factorial, but it also contains the 3 factorial. What I'm going to choose to do here, I kind of want it when we're simplifying, it's probably a good idea to be left with the smallest numbers possible to actually calculate, right? So I could do 6 factorial up to 3 factorial and then cancel out the 3's, but the 5 factorial is a lot bigger, and so the numbers I'm working with will be a lot smaller if I just go like this. If I just do 6 factorial is the same as 6 times 5 factorial, right? And then we're dividing that by 5 factorial times 3 factorial, okay? Because now 5 factorial over 5 factorial is just 1. So I'm left with 6 over 3 factorial. And 3 factorial is not that hard to figure out, right? Versus 5 factorial, which was our other option to cancel the 6, do 6 times 5 times 4 times 3 factorial. Cancel that out, but then we're left with the 5 factorial in our denominator, which is a lot bigger, right? And the 6 times 5 times 4. So this was probably an easier method to go with because we have a smaller factorial to compute. 3 factorial we can do in our heads, right? It's 3 times 2 times 1. It's 6. So this is just 6 over 6, which is just 1. All right. Now, let's take a look at D here. Sometimes students see D and they get a little intimidated because they say it's not a number. But n just represents some number, right? What is n factorial? Well, how do we calculate any factorial, right? How do we do 6 factorial? 6, then 5, then 4, then 3, then 2, then 1. We just multiply 6 by a number that's had 1 subtracted from it each time, right? 6 minus 1 is 5, so 6 times 5. 5 minus 1 is 4, so times 4. 4 minus 1 is 3, so times 3, right? So all a factorial is, in general, n factorial is just n times one number lower than n, right? Times one number lower than that. So if one number lower than n minus 1 is n minus 2, right? Times n minus 3, right? Again, if this were 6, we'd just be doing 6 times 5, 6 minus 1, times 4, 6 minus 2, times 3, 6 minus 3, right? That's all a factorial saying. So do you see how we can make use of that? N factorial over n minus 1 factorial. Well, n factorial is just n times n minus 1 times n minus 2 times n minus 3 and on and on and on. In other words, it's n times n minus 1 factorial. This is just n minus 1 factorial, right? Obviously, it keeps going, but that's what n minus 1 factorial would be. It would be n minus 1 times n minus 2 times n minus 3. So we could start expanding this n, because it's the bigger one. So I'll rewrite n factorial as n times n minus 1 factorial over n minus 1 factorial. N minus 1 factorial over n minus 1 factorial is just 1. And so this actually ends up just being equivalent to n, right? We can make it, maybe a little more intuitive by thinking about numbers. What's 6 factorial over 5 factorial, right? It would just be 6. So n factorial over n minus 1 factorial is just n, right? Okay, let's try out this one. So it wants us to simplify n permute 3, right? Well, what does that even mean? Remember, the formula for n permute r is just n factorial divided by n minus r factorial, right? The number of ways there are to arrange all of the options, but then we want to divide out the number of ways to arrange the things that aren't actually being chosen and therefore aren't actually being arranged in the outcomes we're interested in, okay? So with that in mind, n permute r, our r is just 3, n is just n in this case, and they want us to simplify. So writing out that equation, n permute 3 is just n factorial, because all we have is n here, there's no actual number, over n minus 3 factorial. Now, do you have any ideas about how we could simplify this? Well, is n minus 3 contained within n factorial? It is, right? Because n factorial is just n times n minus 1 times n minus 2 times n minus 3, and then times n minus 4, n minus 5, n minus 6, but we're just talking about n minus 3 factorial there, right? n minus 3 times n minus 4 times n minus 5 times n minus 6 is just the beginning of n minus 3 factorial, okay? And why did I stop there? Well, because my denominator is n minus 3 factorial. So now I've gotten rid of the factorials, right? That's typically our goal here when trying to simplify and work with factorials is get rid of the factorials, right? Get rid of them by canceling them out with one that contains them. So that just gives me n times n minus 1 times n minus 2. And there we go. We've simplified it. We could expand that out if we wanted, but that's not really any simpler than that. So there is our simplified expression for n permute 3. All right, so now it says if 5 pick x equals 20, determine the value of x. So our n is 5, our r is just x, right? And again, n pick r is just n factorial over n minus r factorial. So what they're telling us is that 5 pick x is 20, right? So that means 5 permute x is equal to 20, but it's also equal to 5 factorial over 5 minus x factorial. right? So 20 is equal to 5 factorial over 5 minus x factorial. Now we got to figure out a way to find x. Now this is going to require a little bit of thinking from us here, right? What do we know? We know that 20 is equal to 5 factorial over 5 minus x factorial. And you can kind of see we're not going to be able to cancel out that factorial in this situation, right? Like, this is not 5 factorial, it's 5 minus some unknown number factorial. So it's not like this is, 5 times 4 times 3. It's starting from 5 minus x. And the problem is we don't really know what the x is, right? So if you're thinking, well, could we do like 5 minus x times 5 minus x minus 1 times 5 minus x minus 2? I like that your head went there, but again, we still won't be able to cancel out the 5 factorial because that won't contain 5 factorial, right? It'll have 5 minus x minus 1 factorial. And we don't know what x is. So looking here, let's think about this, because 5 factorial is just a number, and it's not that big of a number. I mean, it's big, but it's 5 times 4 times 3 times 2 times 1, right? You could put it in your calculator, but also 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120. So 5 factorial is just 120 over 5 minus x factorial. Okay, now again, we got to figure out what x is here, but we can start kind of thinking about, we might not get x directly, but think about what this is saying. 120 divided by something is 20, right? And that something is just 5 minus x factorial. So, just rearranging this a bit might not give us x immediately, but at least we might be able to figure out what 5 minus x factorial is, right? Multiply both sides by 5 minus x factorial. So we're multiplying that by 20 will equal 120. Then divide both sides by 20, and we end up with 5 minus x factorial has to be 120 over 20. And 120 over 20 is just 6. So again, we don't know what x is yet. But we know that when we do 5 minus x and then take the factorial of that, we get 6. Now, it's not that hard to figure out what number factorial will give us 6, right? I mean, we can even just kind of reverse the factorial until we find 6. 1 times 2 is 2, times 3 is 6, right? If this had been 24, we would have said, okay, 1 times 2 times 3 times 4 is 24, right? It was a 6, though, so 1 times 2 times 3 gave us 6. Therefore, right, 1 times 2 times 3 is 6, and that's just 3 factorial. So 5 minus x factorial just equals 3 factorial. And therefore, 5 minus x must just equal 3, right? If 5 minus x factorial is 6 and 3 factorial is 6, well, 5 minus x must just be 3. There's no other number factorial that gives us 6, right? That's the nice thing about factorials. It's, 3 factorial is always equal to 6. 4 factorial is always 24. So 5 minus x equals 3. Let me add x to both sides, subtract 3. You can figure out pretty quick that x is 2. And there we go. We got it. X is 2. We could always check our work if we wanted, right? Do 5 permute 2 and see if you get a result of 20, or take your 2 and put it into this equation, right? 5 factorial over 5 minus 2 factorial. Well, that's going to be 120 over 6, right? 120 over 3 factorial, which is 120 over 6, giving us 20. So it works. All right. So this one here, it's found that there are 90 ways that a first place and a second place prize could be awarded in a talent show. How many contestants were in the talent show? Okay, so let's break this down a bit. There's 90 different ways that first and second could be awarded, right? So what that's telling us is how many different possible outcomes there are to choose, well, 2 different things, right? And we're being asked how many options were there to choose from, right? So what it's telling us, 90 ways first and second place could be awarded, is just saying that whatever n is, however many contestants there were 90 different ways to arrange two of them. Because that's really what we're doing here by picking first and second, right? Order matters. If person A is first and person B is second, that's a different outcome if the same two people are flipped around, right? If person B is first and person A is second, it might still be the same two people, but different order leads to a different outcome here. Okay, so that's what it's saying, right? It's just saying that NP2 is 90. And we're being asked to figure out what is n, right? How many contestants were there to choose from? So keeping in mind that, again, NPR is n factorial over n minus r factorial. Well, our r is just 2, and we know that this side of the equation is 90, right? N pick 2 is 90. So that just means we can say 90 is equal to whatever n is, factorial, over n minus 2 factorial, right? And here we go. Now we do have a factorial, right? N minus 2 factorial is contained within n factorial, because n is just n times n minus 1 times n minus 2 times n minus 3, etc., right? So this is one where we can get rid of the factorial and then hopefully be able to solve algebraically. So what is n factorial? It's n times n minus 1 times n minus 2, and I'm going to stop there because the rest of it is just n minus 2 factorial. And I chose to stop there because my denominator is n minus 2 factorial. And so now these can cancel out, and we're left with the fact that 90 equals n times n minus 1, right? And so this is now, look what we've got. We've got a quadratic equation with n, and we could solve this just like we're in Math 20 again, right? So this is saying that 90 equals n times n is n squared, n times negative 1 is negative n. And just like we always would with a quadratic equation, bring everything to one side, factor, right? And then that will make it easy to figure out what the solutions are to this equation, and therefore what the value of n is. So I'm going to bring everything to one side. I'm going to do n squared minus n. I'm going to subtract 90 from both sides, and that equals 0. Okay, and now I know that we have, okay, a quadratic equation here. We need to ask ourselves what two numbers multiply to negative 90 and add to negative 1. Okay, we have the added benefit here of as well of knowing that our two factors actually have to be what's the word I'm looking for? Consecutive, right? One must come right after the other. So that helps us out here as well. Like, for example, like it might be 8 times 9, although obviously it's not. But hey, 9 times 10, that's looking pretty good. Sure enough, right, the two numbers that multiply to negative 90 and add to negative 1 are going to be negative 10 and positive 9, right? So this is just n minus 10 times n plus 9. And that has to equal 0, right? We're just solving a quadratic equation. So now this gives us two separate equations, right? If n minus 10 times n plus 9 equals 0, that's only possible if n minus 10 is 0, and therefore if n is 10, or if n plus 9 is 0, and therefore if n is negative 9, right? Now, that gives us two solutions to this quadratic equation. Are both of these answers to the question we were asked, though? Because we were asked how many contestants were in the talent show. The quadratic equation that resulted does have two solutions, right? Both negative 9 and 10 do make this equation true. But does negative 9 make sense as the number of contestants? Could you have negative 9 contestants in a contest? No, right? So that is an extraneous solution. We can't have negative 9 contestants. So this is an extraneous solution. We'll reject that one. But 10, nothing wrong with that. We could have 10 contestants, right? So there were 10 contestants. okay? And that's often the strategy when we need to solve for an n here in like an NPR type situation. We just use the formula, right? Take advantage of the fact that we can get rid of the factorials by partially expanding and canceling out. And then sometimes it's a quadratic to solve. That's usually easier to solve algebraically. Sometimes you do get one that's like a cubic, and we could use our unit 2 strategies, but they can be pretty tough. So we can also take advantage of the fact that we know whatever the factors are, they're consecutive, right? Which makes it not that hard. Now you should explain yourself. If this is like a written response question, you should say, okay, I know that I like just a quick sentence. I know they're consecutive, but like if we had, stuff equals 150 or something, right? You could explain that the factors have to be consecutive, right? Because that's how a factorial works. So it might be something like we need 3 numbers in a row that multiply to give us 150. Right? N times n minus 1 times n minus 2 equals 150. And then it doesn't take too long to say, okay, so maybe it's, 9 times 8 times 7, or 8 times 7 times 6, or 6 times 5 times 4. And once you figure out what those 3 consecutive numbers are, well, the largest one is just your n. So that sometimes is a strategy that can prove useful. But often we can just do it algebraically by solving like this with a quadratic. I think there's some in the practice, though, where that trial and error method can come in handy. Just make sure you don't just, make it show up. Explain your logic behind it to get full marks on a written response on a diploma or something, okay? So go ahead and try these ones out. These are some practice with working with factorials, simplifying, algebraically working with them, and also one where you're solving for n in a NP2 type equation here, right? It'll be very similar to this one. Okay. So in our last section of this lesson here, we're going to talk about permutations when it's not as simple as just, okay, you've got this number of things and you want to figure out how many ways there are to arrange R chosen from them, right? In these, sometimes there might be limitations on how we're allowed to arrange them. So sometimes the ways we can arrange things are limited by specific conditions that need to be fulfilled. So some examples you might see, right? I mean, this is not a exhaustive list. There's definitely more. But, things like 2 people must or must not sit next to each other in a group photo, right? Or a certain digit must or must not be used in a phone number. No letters can be repeated on a license plate, right? A password must begin with a certain letter. Okay, now we're going to apply all the same logic. We're just going to consider how these restrictions or limitations affect the number of choices we have or the number of options available to us for each kind of spot that we're putting stuff into. Okay, so when dealing with these restrictions, we're mostly just still going to use the fundamental counting principle. We're just going to recognize that there's, different limitations for different spots based on the restrictions being placed on our permutations here. So we just need to consider how they affect the number of options available to us, and then evaluate the same way we always would by considering the number of options for lack of a better word, for each spot, and then use the fundamental counting principle. Word of advice here, okay, I strongly recommend deal with the restrictions first. Consider the conditions first. That is always going to make life easier, okay? Deal with those first, and then the ones that don't really have rules about, you kind of fill in with, just whatever is left to choose from. So always go with the restrictions first so that you've dealt with those, and then everything else doesn't have a restriction, so you just fundamental counting principle your way through it. Okay, let's try it out, see what it looks like. So a vehicle license plate in a certain country consists of 3 letters followed by 3 digits. How many license plates are possible if the number 0 cannot be used and no letters can be repeated? So like I said, we just got to think about, okay, how does this limit our choices? So I'm just going to start out here, 3 letters, 3 digits. So 3 letters, 3 digits, and we're going to fill that in, okay? Now, no letters can be repeated. So if we think about that, okay, that's the only condition on our letters. But all that means is that once we've used a letter, we can't use it again. So there are 26 options for letters, but once we use one, we only have 25 left to choose from, then 24, then 23, right? Every time we use a letter, we lose that letter, okay? So when we don't have repeats, when we're not allowed to repeat letters, I have 26 to choose from at first, right? That leaves me with, though, like say I use A. Now I can't use A, I can only use B through Z. So that leaves me with 25, right? Say I use B. Now I can only use C through Z. So that leaves me with 24, right? That represents letters with no repeats. That's how we would arrange 3 letters if we weren't allowed to repeat any. If we were allowed to repeat, it would just be 26 times 26 times 26. Okay, now followed by 3 digits, but the number 0 cannot be used. So how many choices do we have for digits? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 options. And it doesn't say the digits can't be repeated, right? So we could repeat the digits. It specifically says the letters can't be repeated, right? No letters can be repeated, but it doesn't say the digits can't. So that means how many options do I have for my first digit? Well, 9, 1 to 9, right? How many do I have for my second digit? Still 9, you're right, because I can repeat them, right? So if I wanted, I could go 1, 1, 1 or 2, 2, 2, right? Or 1, 1, 2. Okay, 9 options again for the third one, right? So 3 digits with no zeros. Okay, but repeats are allowed. Repeats allowed. So I'm not losing a digit every time I choose one. So that's going to give us, if I multiply that out, okay, 26 times 25 times 24 times 9 times 9 times 9, it gives me 11,372,400 different possible license plates. Okay, so notice nothing has fundamentally changed in our thinking. We're just taking the time to consider, all right, how do these restrictions affect the choices available to us? And then it's still just the good old fundamental counting principle, right? If there are P ways to do one thing and Q ways to do another, there's P times Q ways to do both things. Here we just have 6 things we're doing, which is choosing 3 letters with no repeats and choosing 3 digits with no zeros, but repeats are okay. All right, let's try out another one. So it wants us to determine the number of different arrangements of the 6 letters in the word answer that, for part A, they must begin with an S. So that's our restriction, right? So like I said, let's just let the restriction tell us what to do, tell us how our options have changed, right, compared to if there were no restrictions, and then we'll fill in the rest. So we've got 6 letters, 6 different letters, right? Normally, there would be 6 factorial ways to arrange them, right? 6 options for the first spot, 5 left for the second, 4 for the third, and on and on and on. But here, it must begin with an S. So out of these 6, how many choices do I have for my first spot? Right, I've only got 1. I can only use the S here. So I've got 1 choice for my first letter, right? That's it, okay? But then I'm allowed to use any of the other 5 that are left. I've used the S, but I've still got A, N, W, E, R. I could choose any of them to go here. So I've got 5 options left here, then 4 options left here, then 3, then 2, then 1, right? One way to look at this is that we're not interested in how to arrange answer. The S is placed for us, and then we're really asked, how many ways are there to arrange and were if after that, right? So that's why we end up with just 5 factorial, because really the S is locked in, and it's really just about how many ways can we arrange these then, right? So that kind of makes sense. It just ends up being 5 factorial because there's 5 letters that we're actually allowed to move around, okay? So 1 times 5 factorial gives us obviously 5 factorial, which is 120. All right. What about if it must begin with a vowel? Well, let's look. The vowels are A, E, I, O, U, right? So I do see 2 vowels. So again, let's just first, we've got 6 letters to arrange. Now for that first one, it needs to begin with a vowel. So how many options do I have here? I've got 2, that's right. I could put an A there, or I could put an E there. And then after that, what are my choices? Well, I've chosen one of the vowels, right? Careful, sometimes students want to say 4 here, but we're not putting the A and the E there. We're putting the A or the E there, right? So I have 5 choices to put here, right? 5, 4, 3, 2, 1. So it's just 2 times 5 times 4 times 3 times 2 times 1, which is 2 times 5 factorial, or 240. This actually makes a ton of sense, right? Because it's actually a lot like A, except we could do all of this, right? We could do all of this, arrange the 5 letters that we didn't start it with, but then we can do it again with the other letter, right? We could do A, E-N-W-E-R, no, E-N-W-R, what am I missing? S, right? There's 5 factorial ways to do that. But then there's also, I could have started it with the A. Sorry, with the E. And then there's 5 factorial ways to arrange those, right? So I get 2 5 factorials, right? 1 from starting it with A, and how many ways can I arrange the other stuff? 1 from starting it with E, and how many ways can I arrange the other stuff? Okay, but notice, right, same logic there. I started with the restriction. So I started with the fact that it had to begin with a vowel, and then I let the fundamental counting principle take me through the rest, the stuff that didn't have restrictions on it. All right, begin with a vowel and end with a consonant. So let's look at this. We've got 6 spots, so to speak. Okay, I'm going to deal with the restrictions first. So it must begin with a vowel. There are 2 vowels in this word, A and E. So I have 2 options for my first spot. There's 2 ways to start this with a vowel. So when doing the fundamental counting principle, right, if there's P ways to do one thing and Q ways to do another, there's P times Q ways to do both. 2 ways to choose a vowel, so I'm going to have to multiply whatever's in here by 2. And end with a consonant. Well, there's N, S, W, R. There's 4 consonants, right? So I can put 4 letters here. There's 4 options for what goes in the last spot. Now think about it, right? We've already chosen 2 letters, hypothetically here, right? We picked one of our 2 to put here. We picked one of our 4 to put here. So how many letters do we have left, right? You know, say we use A and N. We've got 4 letters left to choose from, right? So we've got 4 times 3 times 2 times 1. 2 times 4 times 3 times 2 times 1. Again, notice what I did there. I dealt with the restrictions first. Begin with a vowel, 2 ways to do that. End with a consonant, 4 ways to do that. And then I worry about, all right, what would be left after that? If I put a vowel here and a consonant here, how many other letters will be left now to work with, and how many ways are there to arrange those, right? Unsurprisingly, it's 4 factorial. After we put a vowel and a consonant here, we're left with 4 letters, and there's 4 factorial ways to arrange 4 letters. So that gives us 192. All right, let's try this one, which is revisiting 2A with a twist. So this one says repeat 2A, but for a 4-letter arrangement chosen from the 6 letters in answer. So be careful about that distinction there, right? We're not going to be arranging all 6 letters now. We're going to pick 4 of them and arrange just those 4. So we can choose any 4, okay, but we're not choosing all 6. So let's think about that. Well, again, 2A, it said begin with an S, right? So I still only have one option. It has to start with an S, right? But then I've used my S. I have 5 letters to choose from still, right? I still have 5 letters to choose from. Then I've got 4 left to choose from. I've used another one, so now I've got 3 left to choose from, right? Notice it doesn't go all the way to times 2 times 1, right? But that's because we're only choosing 4 letters out of the 6, okay? So there will be 5 times 4 times 3 ways to choose them. That's going to give us 60, okay? And again, another way to look at it is you've got one option here, and then you're just looking how many ways are there to arrange 3 letters chosen from 6 options, right? That would be, 3 letters chosen from 5 options. So that would be 5 choose 3, which would be 5 factorial over 5 minus 3 factorial, which would be 5 factorial over 2 factorial, which is just 5 times 4 times 3 times 2 times 1 over 2 times 1, we don't care about the order of the things that aren't chosen, right? It's that same logic we were talking about earlier. Whoopsies, I used a C. That should be a P. Sorry about that. I was in next lesson already in my head. That should be a P. Okay, but there we go. All right, shall we try one from an old diploma? Let's see what this is all about. Okay, so the number of possible placements of the players for the photo is. Again, I like to often read the question first because then I know what I'm looking for. So let's read this. For a team photo, 9 volleyball players are to stand in a line. The photographer will place the shortest player at one of the two ends of the line. Ooh, at one of the two ends. So careful. That means they could go on, one end, or they could go on the other end. But the tallest player will go in the middle. So let's think about this. Again, we've got 9 players. We want to know how many ways are there to arrange them that satisfy these conditions we have to satisfy. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, we do know that the tallest player has to go in the middle, right? So we know that the tallest player, 1, 2, 3, 4, 5, right there would be the middle. Yeah, 4 on either side of them. So that's our tallest player. Only one choice for the middle, okay? But we could put the shortest player here, right? Or we have a whole nother situation. Again, tallest player in the middle, but we could also have put the shortest player here. We could put the shortest player on the right end, or we could put the shortest player on the left end. So there's multiple ways you could have reached this idea, right? Do you necessarily have to do it all out twice? Not necessarily. You could be able to recognize, okay, but there's 2 options for what the end is. So you could have done it once and then multiplied it by 2 factorial, because there's 2 ways to place them on the end, right? They could go here, they could go here. But we could also just treat it like 2 separate cases, right? How many ways are there to arrange them if the shortest player goes on the left end? Then, how many ways are there to arrange them if the shortest player goes on the right end? And then we can add those up to get the total number of ways they could be standing, right? It's like 2 separate cases. So essentially, that's how I'm approaching it here with my setup, right? There's 2 cases. We could have the short player on the left end, or we could have them on the right end. So if we can find the number of arrangements where the player is on the left end, and then find the number of arrangements where on the right end, and then add those 2 numbers together, we'll have the total number of possible ways that they could do this, right? So we've dealt with our restrictions, right? Those were the only restrictions. Shortest had to be on one of the 2 ends, and tallest had to be in the middle. So how many players are left now to fill in the gaps? We've taken care of the shortest, we've taken care of the tallest. We had 9 to begin with, so there's 7 left, right? So this is times 7, times 6, times 5, times 4 left to go here, 3 left to go here, 2 left to go there, and 1 left to go there. So you can see this is actually just 7 factorial, right? I mean, there's extra 1s in there, but it's mathematically equivalent to 7 factorial, or 5,040. Now, of course, we're going to get the same result down here because there's 7 players left to deal with. So 7 times 6 times 5, 4 left to go there, 3 left to go there, 2 left to go there, and only 1 player left to stand in that spot. So once again, it's 7 factorial, which is 5,040. So what's the total number of ways? Well, if there's 5,040 ways where they're standing on the left, and then another 5,040 ways if we put them on the right, the total is just going to be 5,040 plus 5,040, which is 10,080. Now, sometimes for this type of question, students will say, well, how come we didn't multiply them, right? And that's because this excludes this, right? If we do this, we did not do this, right? If the player went on the left and the player went on the right, that's kind of 2 different situations. It's not like we need to multiply all of these possibilities. It's not like for every, outcome here, we could have also done this many different ways, right? It's not like for all 5,040 of these arrangements, we could have done all 5,040 of these arrangements, right? We couldn't have. If the player's on the left, they're not on the right, okay? So that's why we're adding them here, because there are 5,040 ways to do it this way, but there's 5,040 ways to do it another way. So we need to add those up, right? This is not, for these 5,040 ways, we can't do it another 5,040 ways each. So it doesn't make sense to multiply there. So our answer is B, 10,080. So another common type of restriction we can have is that, yes, we're going to rearrange stuff, but we have to keep certain things together, okay? So when two things must be together, when we see that terminology used, think about what that means for the arrangements, right? If we have to keep them together, we can basically treat them like one object, right? We essentially group them together and treat them like one object because we're not allowed to split them up. So for example, right, if 5 friends want to sit together in a row, but Gian and Andreas want to sit together, well, that means we're not allowed to split up Gian and Andreas, right? It's kind of like we just have one person, quote unquote. It's Gian and it's Andreas. Now, we're allowed to move them there, or even there, but we're not allowed to take Gian and Andreas and move them separately. So do you see how it's almost like they're one object now, right? They can be in between people or they can be on either end, but there can't be people in between them. They need to be together, okay? So since Gian and Andreas are grouped together no matter what, we can look at them as being one person that can fit anywhere around or in between the other individual people. So how many objects are we really dealing with here? We're really dealing with 4, right? We've got Gian and Andreas, and then 3 other people that can be moved around however we want. So we're really just dealing with, it's like we're dealing with anyway, 4 objects to arrange instead of 5, because we can't split those 2 up. Now we can arrange 4 objects in 4 factorial ways, right? We could do 4 times 3 times 2 times 1, right? Treating them like one person. Now, there is a very important caveat to that, okay? There are actually, though, twice as many ways to arrange them than just 4 factorial. Because there are 4 factorial ways to arrange them. That's true, to arrange 4 objects, right? But for each of those 4 factorial arrangements, where Gian and Andreas were together, it could have been Gian Andreas or Andreas Gian, right? It just said they had to be together. It didn't say Andreas had to be on the left or on the right and Gian had to be on the left, right? So yes, we could do all the 4 factorial ways to arrange these 4 objects, but then we actually have twice as many because then we could do it all over again by switching these 2 around. And that does give us a different arrangement. So altogether, it's just 2 factorial times 4 factorial. There's 2 factorial ways to arrange Gian and Andreas, and then there's 4 factorial ways to arrange that group within the 4 quote-unquote objects that we essentially have. So it's 2 factorial times 4 factorial, which is just 2 times 24, which is 48. Okay, so 4 factorial ways to arrange 4 objects, because really they're like one object, but then also 2 factorial ways to arrange those objects within that group, giving us a total of 48 ways we could do it. Let's try this one out. So it says, how many arrangements of the letters in the word daughter can be made if all of the vowels must be kept together? Okay, so let's just group them. We're not allowed to split them up. And we can think of them as basically being one letter, right? We've got A, U, E. Those are our 3 vowels. And they're not allowed to not be next to each other, okay? What does that leave us with? It leaves us with D, G, H, T, R, right? So do you see how it's kind of like we've got one letter, right? And then 2, 3, 4, 5, 6, right? We really have here 6 objects that we're allowed to arrange, right? So it's like we have 6 letters because we're not allowed to split up those A, U, and E, okay? Now, 6 factorial is 720. There are 6 factorial ways to arrange these 6 quote-unquote letters. However, be careful, because for that's just how to arrange these ones where, for example, it's AUE. But we could also have done UAE or UEA or EAU or EUA and on, right? There are 3 factorial ways to arrange the AUE within this group. So yes, we're not allowed to split them up. We're going to keep them as a group, but within that group, they could be arranged 3 factorial ways. And that means for all 720 ways there are to arrange these 6, letters, there are another 3 for every single one of those 720, there's 3 factorial ways we could have arranged the AUE. So that means, right, so I'll just say, but there are 3 factorial ways to arrange the AUE. So we need to multiply that 720 by 3 factorial, right? So really we have 720 times 3 factorial, which is just 720 times 6, which is 4,320. Okay, and there we go. All right, let's look at the reverse of this, when there are objects that must not be together. Now, these can kind of make your head spin a little bit at first, because there are many, many possible alignments when you think about it, right? If you give it enough thought, you realize, holy cow, there are a lot of ways to do this, right? It can be difficult to even imagine all of them. You can kind of lose track. So just to get you thinking about how tough this could be if we didn't, come up with a better way, suppose we have 10 cars with 3 of them being blue. How many ways could they be arranged so that no blue cars are next to each other, right? There's a ton of ways this could happen, and we can't really use our fundamental counting principle to easily find them, because it's not saying they must be together, it's saying they can't be together. So that's tough. We've got 10 spots, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they just must not be together. So we could put a blue one here and a blue one here and a blue one here. That's true. But we could also put a blue one here and 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 a blue one here, right? Do you see where I'm going with this? And that's just doing these 2 in this spot. And then we could oh boy, we could just keep doing that. And all that does is that just tells us all the ways if we use these specific spots. Now we got to think about, okay, but that could have gone there and this could have gone there, and it gets overwhelming pretty quickly. Luckily, there's something we can take advantage of here to actually make it a lot simpler than that kind of mind-boggling thing we'd have to think about there, okay? When we're dealing with a situation where things cannot be together, we can take advantage of this fact. If we take the arrangements where they are together, and we add the arrangements where they are not together, well, what do we get? We get every single possible arrangement, right? No matter what arrangement you have, it fits into one of those 2 categories. It's either an arrangement where they are together or where they're not together, right? It can't be both of those things at the same time, or it can't be neither of those things. If it's an arrangement where if it's not an arrangement where they are together, well, then automatically it's an arrangement where they're not together, right? If it's not an arrangement where they're not together, then automatically it's an arrangement where they are together, right? So if we take all the ones where they're together and all the ones where they're not together, we get every possible arrangement. There's an old saying that everything in the universe it fits into 2 categories. It's either a potato or it's not a potato, right? Which is true. Right? If it's a potato, then it fits into the potato category. If it's not a potato, it fits into the not a potato category. Same idea here. All possible arrangements can fit into one of these 2 categories. They are together or they're not together. So add up those 2 categories and you get all possible arrangements. It can't be in both categories either, right? How could they be together but not together? Okay? So that's the fact we're going to take advantage of to actually make this a lot easier, because we've seen how it's not too bad to figure out the arrangements where they are together. We just group them up, right? Figure out how many ways there are to arrange the quote-unquote objects we're left with if we treat them as one group, and then also deal with the fact that we could arrange them multiple ways within that group, okay? But we'll just figure out all possibilities. We know how to do that. It's just n factorial. Take away the ones where they are together, and what we'll be left with is the ones where they're not together. let's try walking through this process with an example here. So 5 people, A, B, C, D, and E, are going to sit on a bench. How many ways can they be arranged if there are no conditions? So how many ways can we arrange 5 people, right? Well, 5 factorial, which is 120, right? I mean, you could go 5 people in the first spot, 4 in the second, 3 left in the third, 2 left in the fourth, and only 1 person left in the last spot. Left to choose from, I should say. Okay, so 120. Now, how many ways can they be arranged if A and B must sit together? Well, if A and B must sit together, let's just treat them like one person, keeping in mind that we could also have BA, right? So we actually are going to have 2 factorial ways to arrange them within this group. But that means we really just have how many people, how many objects to arrange? Right, it's like we have 4 people, right? 4 objects to arrange, okay? So there are 4 factorial ways to arrange 4 things, 1, 2, 3, 4. But there's really 2 factorial times as many, because we could also have, for every one of those 4 factorial ways, we could do AB or BA, right? So there's actually twice as many arrangements as 4 factorial. Okay, so we could say 2 factorial times 4 factorial, right? This is number of ways to arrange the AB within that group, okay? And then this is ways to arrange A, B, C, D, E, okay? So we got 2 factorial times 4 factorial. Well, that's just 2 times 24, which is 48. Okay, so there's 120 total ways they could possibly be arranged, all 5 people, 120 ways to arrange them. In 48 of those arrangements, they are together. That's what we just found. We found all of the possible ways where they are sitting together. There's 48 of them. So if there's 120 ways total for them to be sitting, and in 48 of those ways, they are sitting together, how many ways are they not sitting together? Well, take 120, the total possible ways, and subtract off all the ones where they are sitting together. So, right, we've got, again, the total is 120. Together, there's 48 ways they could be sitting together. So our number of arrangements where they're not together is going to equal 120, right, the total, minus the ones where they're together, minus 48, okay? So that equals 72, right? So there are 72 ways they could sit where A and B are not together. And there we go. All right, let's try another one where they must not be together. So a car dealership has 10 different cars. 3 of them are blue, and the owner does not want all 3 blue cars right next to each other. How many arrangements are possible that will satisfy their conditions? Okay, so again, we could sit here and, start thinking about this problem where we don't have all 3 together, okay? Or we could say, well, we can figure out the number of arrangements where they are together and then subtract that from all of the possible ways they could be arranged, and all we could be left with then is the number of ways where they're not together, right? So there's our plan. Let's call it step 1. Find total possible arrangements. Okay, well, there's 10 cars. How many ways are there to arrange 10 things? 10 in the first spot, 9 left for the second spot, 8 and on, right? It's 10 factorial. So that is 3,628,000. Okay, there we go. That's the total number of ways we could arrange those cars. And that includes the ones that we're trying to get, the ones where they're not together. So to get at what that number is, let's figure out how many ways where they are together. So we'll find ways where they are together. Okay, so look at it this way, right? There are 3 blue cars. They are together for us here. And then how many are left? There's 7 other cars. So how many cars is this kind of like, right? If these must be stuck together as one quote-unquote car, we've got 1 here, 7 here. So it's like there's 8 objects to arrange, right? It's like there are 8 things, 8 objects. Whoops, that's not how you spell objects. Okay, it's like there's 8 cars to arrange here. Well, there are 8 factorial ways to arrange 8 objects. What am I forgetting, though, if I just do 8 factorial? Right, these 3 blue cars, okay, they're all different, so they could be arranged in 3 different ways. 3 factorial different ways. Okay, so we need to do 3 factorial times 8 factorial. This is how many ways there are to arrange our, 8 objects. Okay, but then this is how many ways there are to arrange the blue cars within that. So for every single one of those 8 factorial arrangements, we could have done up to 6 different arrangements of the blue cars. 3 factorial is 6. Okay, so this is 6 times 8 factorial is 40,320, which gives us 241,920 ways where we could arrange the cars and the 3 blue ones would all be together, which is exactly what we don't want. We want to find all the arrangements where they are not together. Luckily for us, we found the total possible, and we found the ones out of those total where they are together. So find arrangements where they are not together. Okay, and since not together plus together equals total, right, then not together is just going to be take our total and subtract the ones where they are together. And all we'll be left with is the ones where they're not together. So there were 3,628,000 total possible ways we could have arranged those 10 cars, right? And in 241,920 of them, they were together. So our not together arrangements is going to be whatever 3,628,000 minus 241,920 gives us 3,588,480 possible ways to arrange them where they are not together. And there we go. Okay, go ahead and try this one out. This gets you thinking with some restrictions and stuff, okay? In how many ways can 4 girls and 2 boys be arranged in a row if the boys must be on each end of the row, right? If the boys must be together, okay? And then I encourage you, try out a couple more as well. I just put these 2 in here as some try nows type things, but you can pause the video, take some time, part 10, number 10 probably has a C and a D that you could try as well. Take a little break from my voice, solidify the concepts, and then we'll finish up by talking about what happens when you have repeats of the same thing, or what we call identical elements within a group of options that we're trying to arrange. All right, so to get us thinking about this, I want you to consider this, okay? How many ways are there to arrange the letters in the word all, A-L-L? So we might think, okay, there's 3 letters, and we've seen this before. If there's 3 things, there should be 3 factorial ways to arrange them, right? And 3 factorial is 6, 3 times 2 times 1, okay? But if we try to map out these 6 arrangements, here's what we get. A-L-L, and then I'm going to switch the 2 L's to get A-L-L. And then I'll put an L in the first spot, so L-A-L. And then again, I'll switch the 2 L's to get L-A-L. And then I'll do 2 L's in a row at the beginning, so L-L-A. And then I'll switch those 2 L's to get L-L-A, right? Now you're probably noticing not all of these are actually different arrangements, right? They're not actually distinguishable from each other. this is not any different looking than this. There's no way to tell these two apart, right? They're the same word. It's the same outcome. So switching those two L's around actually didn't give us any new arrangements, okay? Some of those aren't really different arrangements at all. They're just repeats of ones we'd already seen because we thought about switching the two L's, but that doesn't actually give us a different outcome in this case, does it, right? Yes, order matters, but not if the two things you're switching are identical, okay? So since there are two L's in the word, switching the placement of those L's doesn't actually give us a new unique arrangement. For example, right, like changing ALL to ALL, I tried to use colors there to highlight the quote-unquote different L's, right? It's still giving us the same outcome. It's still giving us the same word. It's not really a unique, distinguishable arrangement. So if we get rid of the repeats, what do we have, right? We do have different arrangements, but we don't have 6, right? Take out this repeat, take out this repeat, and take out this repeat, and you can see that we really just have 3 unique, distinguishable arrangements. So we really only have 3, right? And why did we get too many? What was our problem by using 3 factorial? Well, when using 3 factorial, we were thinking that our 2 repeated L's could be arranged in 2 factorial ways, right? It's 2 letters. We're used to saying that 2 things can be arranged in 2 factorial ways. But that logic doesn't really hold up here because arranging the 2 L's by just switching them with each other doesn't give us a new word. And so that gives us 2 factorial times too many unique arrangements for the actual problem, right? We have 2 times too many, which comes from the fact that we thought, oh, we could switch all the L's around, giving us, another 2 factorial arrangements, okay? So we need to divide by those 2 factorial extra arrangements from the identical elements being identical parts of a set, right? Each letter is an element of a set here, so the L's are 2 identical elements of this 3-letter set. So to get the real number of unique arrangements, we would need to take, here's the breakdown, right? Take 3 factorial, that's how many ways there are to arrange 3 unique letters, but that's going to be 2 factorial times too big because we're considering in there, right, just switching the L's around. And there's 2 factorial ways to switch the L's around, but none of them are different. So it doesn't actually give us new arrangement. So we have to divide that out, right? We're multiplying by that 2 factorial here that doesn't actually belong because switching the L's is not a different arrangement. So divide it out to get rid of it, leaving us with the correct number of unique ways to arrange those 3 letters if 2 of them are identical, which is 3, which is exactly what we got, right? Now, this logic works no matter how many repeats there are, because if we have identical elements, then always included in our, n factorial is going to be all the ways where we just switched around those identical elements, which doesn't actually give us new, unique arrangements of the letters, right? So if, for example, there are 3 identical elements, then treating them all as unique will give us 3 factorial, or 6 times more unique arrangements than are actually available, right? I mean, if we take, let's just pretend all is spelt with 3 L's, right? Right off the bat, we can see even with just A in front, if we just do, 4 factorial, we can tell that's too many, because switching these 3 L's in the 6 different ways we could switch them around, the 3 factorial ways we could arrange them, that doesn't give us new arrangements, right? There's really, what we would do here is we would say, if we just said 4 factorial, right, we'd need to divide by 3 factorial, because for each of those 4 factorial ways, we were acting like there were 6 ways to arrange the L's, but there weren't, right? There's not. Switching those L's around doesn't actually give us a new arrangement. Okay, so it also holds when there are multiple repeated elements. For example, in the word tattoo, we've got 3 T's and 2 O's. Now the 3 T's are going to give us 3 factorial, or 6 times too many unique arrangements if we treat each T as being unique, right? So how do we correct for that? Well, let's just divide the total number of arrangements of all, if all letters were unique, by 3 factorial. right? We'll divide the total. We'll treat it like it's normal, treat it like this is 6 letters, but then divide out the extra arrangements that we're getting just from switching around the t's in the 3 factorial ways that there are to arrange those 3 identical t's, right? There's also 2 o's. What are the 2 o's going to do? They're going to give us 2 factorial, or 2 times too many unique arrangements if we treat each o as unique. And so to account for that, we'll have to also divide the total number of arrangements, if all letters were unique, by 2 factorial, or 2. So putting that together, the number of unique arrangements of the letters in the word tattoo is going to be 6 factorial over 3 factorial, right? Dividing by the 3 factorial accounts for how many extra arrangements we're getting because of the identical t's, that switching around doesn't really give us a new word, right? And we're dividing out the 2 factorial ways there are to just switch around the 2 o's, which again, switching them around doesn't actually give us a new unique arrangement of letters that we could distinguish, okay? And so that's how we can deal with it. Basically for these, my advice is essentially pretend the repeats don't make a difference. We're actually not going to change anything about how we do, really. We're going to solve it like there really are 6 unique letters here, and then we'll account for the repeats, right? So that's typically the strategy here. Basically, pretend the repeats don't make a difference up until the end, and then you can divide out those repeats that you know you've really had all along, right? So in general, we can find the number of unique arrangements when there are identical elements this way. So if you're arranging n things and there are repeats within those n things, n factorial, but then divide by each repeat for how many there are. So all it's saying is that if you have n items to arrange, but there are A of one kind that are identical, B of another kind that are identical, C of another kind that are identical, and so on, we could have more than 3 identical elements, then you can find the number of unique arrangements with this equation, right? So just like we did here. There are 6 letters, so there's 6 factorial ways to arrange them, but there's 3 identical t's, and there's 2 identical o's. So we'll divide by 3 factorial, 2 factorial, because we're getting 3 factorial times too many from the identical t's that switching around doesn't really make a new arrangement, and 2 factorial times too many from the identical o's, where switching those around doesn't really make a new arrangement. Okay, let's try it out here in some words with repeated letters, identical elements. All right, so first up, in how many unique ways can you rearrange the letters of the following words? First up, boom. All right, well, there's 4 letters, right? There are 4 factorial ways to arrange 4 letters, okay? So 4 letters, but we'll make note that there are 2 identical O's, right? And switching those around doesn't actually give us a new arrangement, okay? So there are 4 factorial ways to arrange the 4 letters, but included within those 4 factorial ways are actually a factor of 2, right? There's 2 factorial of them where all we did was actually swap the 2 O's, and those aren't actually new arrangements. So we're going to divide by those 2 factorial. See what I mean? Right? Deal with the 4 letters, 4 factorial, and then account for the fact that 2 are identical. So 4 factorial over 2 factorial, well, 4 factorial is 24, 2 factorial is 2, so there's actually only 12 ways to arrange them, which really makes a lot of sense, right? There would be 24 ways to switch these 4 letters around, but in half of them, all you would have done is this. Swap the 2 O's, right? I mean, some of them might look like this, but still, that's not actually 2 different arrangements, right? So we're getting twice as many as we actually should. That's why we're dividing out the 2 factorial. Okie doke. Cheeses. Now careful, I see a couple repeats here. I see 3 identical E's, and then I also see 2 identical S's, okay? So there are 1, 2, 3, 4, 5, 6, 7 letters. So there's 7 factorial ways to arrange 7 letters, but we're going to get 3 factorial, or 6 times too many, because of the fact that 6 factorial of those just come from swapping around the E's, right? And then another 2 factorial just from swapping around the S's. which again doesn't give us different arrangements. So it's 7 factorial, but then we need to divide by the 6 factorial, 2 factorial. So that gives us 5,040 over 6 factorial is, I gotta figure that out really quick. Sorry, I thought I had it calculated. 720, I should know that. 720 times 2. Okay, giving us, if I divide 5,040 by 720 times 2, it's 5,040 over 1440, which gives us 420 unique arrangements. Okay, so yes, there's 5,040 ways to arrange in 7 letters, but you'll only be able to tell 420 of them apart if you've got 3 identical letters and then another 2 identical letters. Ooh, look at this one, Mississippi. Holy repeats. I see a lot of identical elements here. Let's count them. Let's do I's. I see 1, 2, 3, 4 identical I's. So 4 I's. I see 1, 2, 3, 4 identical S's. And then I see 2 identical P's. Okay, and how many letters do we actually have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 letters. So there are 11 factorial ways to arrange 11 letters. But we're including too many to actually figure out the unique arrangements, because 4 factorial of those just come from swapping around the I's. 4 factorial of them just come from swapping around the S's. And 2 factorial of them just come from swapping around the P's. Okay? I shouldn't say that many of them, but a factor of that many, right? We multiplied by the 4 factorial ways there were to arrange the I's, but none of those are actually different. So we're dividing those out. So this gives us 39916,800. So 39,916,800. 4 factorial is 24. 4 factorial is 24. And 2 factorial is 2. So divide that number by whatever you get in the denominator there, right? 24 times 24 times 2. It's 1,152. So we've got 39,916,800 over, this comes out to 1,152. Dividing those, I got 34,650 unique distinguishable arrangements of the word letters in the word Mississippi, where you could actually tell the arrangements apart. Okay, let's try one that combines identical elements, so repeats, with some restrictions. So putting together all the stuff we've talked about in this lesson, essentially, right? Now remember what I said. When dealing with restrictions, do the restrictions first, right? Deal with those first and then fill in the rest where you don't have restrictions. And also, yes, we have repeats, but we're going to deal with that at basically the end, right? Pretend the repeats don't matter, the identical elements don't make a difference, and then at the end we can divide them out, okay? So let's just kind of do this step by step. We're going to figure out the number of distinguishable arrangements of the word McMurray that begin with Y. I'm going to do that first, as if it doesn't matter that there's 2 M's and 2 R's, okay? So MCMURRAY, okay? Now, if it has to begin with Y, how many choices do I have to put here? Just one. There's only one Y in McMurray, right? So I'm going to put 1 there. Now that leaves me with, how many letters are actually in McMurray? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I've got 7 left. I already used the Y, leaving me with 7, 6, 5, 4, 3, 2, 1. Unsurprisingly, it's 1 times 7 factorial, right? If the Y is locked in the first spot, then it's really just how many ways are there to arrange the other 7 letters, which is 7 factorial. And so this gives us 5,040. But we need to be careful. Okay, but there are 2 identical M's. And there are 2 identical R's. I don't think I'm missing any others. So what we need to do then, okay, is take our one, where we essentially thought about, okay, ignoring the repeats for now, that's how many ways there are to arrange them, but we have a factor of 2 factorial and 2 factorial times too many, because 2 factorial and 2 factorial of those possible different arrangements that we were multiplying by are actually just switching around the m's and switching around the r's. So we actually have 5,040, sure, but we need to divide it by 2 factorial times 2 factorial. Okay, and that's going to give us 5,040 over 4, because 2 factorial is 2, so 2 times 2 is 4, giving us 1,260 unique arrangements of the letters in the word McMurray that begin with Y. All right, let's look at the number of distinguishable arrangements of the word McMurray now that begin with an M. Okay, so there's kind of 2 ways you could go at this. I'm going to just stick with, let's just 1, 2, 3, 4, 5, 6, 7, 8. Okay, now there are 2 M's. So what you could do is you could put the 2 here. You could also recognize that actually those really aren't 2 different outcomes, right? Putting one M there or putting the other M there doesn't actually make a difference. It's still, it won't be distinguishable, right? By putting one M versus the other. So I'm gonna go with the method of, hey, there's 2 M's. Okay, I'll worry about the identical stuff at the end. So 2 M's, and then I'm left with 7 other letters, right? So 2 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, again, if the M is locked in at first, there's 2 different M's we could use. So really it just becomes 7 factorial, the 7 factorial ways there are to arrange the other letters, times 2 for the 2 different M's. And I know you're probably screaming at your computer right now, but the 2 M's are the same, okay? I know, but with these, it's typically the best approach, or maybe the least stressful approach, is to just pretend they don't matter, keeping in mind that at the end we can divide out all the extra arrangements we've come up with because of the fact that we treated them as unique, okay? So that gives us 10,080. But again, there are 2 M's that are indistinguishable, and there are 2 R's that are indistinguishable. So switching those around doesn't actually give us different arrangements. So we need to take our 10,080 possible arrangements and divide by the fact that a factor of 2 and another factor of 2 that we've included are actually not distinguishable, right? We multiplied by the 2 factorial because that was thinking about switching around the 2 M's. We multiplied by another 2 factorial, a factor of that many different arrangements where really all we had done was switched around the 2 R's. So that's 10,080 over 4, giving us 2,520. Okay. Now, another way you could have approached this is you could have recognized that, hey, this isn't actually 2 different options. They're both M's, right? So you could have not included the 2 there. But keep in mind then, that means you could have made that a 1, right? Since the 2 M's are essentially the same choice. Keep in mind though, that means you've dealt with it already. You've already dealt with the repeating M's there, so you wouldn't divide by the 2 factorial here for the M's. Okay, you've already done that by putting a 1 here instead of a 2. So just keep that in mind. That is sometimes a thing students prefer to do. Notice we'll get the same result because here we multiplied by an extra 2 that we shouldn't have because the 2 M's aren't actually different. And we took care of it by dividing that extra 2 out, right? So if you were to acknowledge that the 2 different M's aren't actually a different choice, that's great, but now you don't need to divide out by it later. You've already taken account of it. So that's why I personally like to just, we'll worry about the identical elements. Once we've figured out the number of ways to arrange it, if there weren't identical elements, we can then just divide out the extra factors that we have because of the identical elements. All right. How about the number of arrangements of the word McMurray that have the R's together? Okay, so really putting together all the stuff we've talked about, right? Let's group the 2 R's. So I'm going to group the 2 R's, and I'm going to treat them like one letter because they have to be together. So you've got our RR, our M, C, M, our U, our A, and our Y, right? So we could kind of look at this as like having 7 letters, right? 7 letters. We've got this one and then these 6, okay? Now, again, we've got options here. We could say, okay, there are 7 factorial ways to arrange 7 letters. But within our group, there are 2 factorial ways to arrange them. Now, this goes back to what I was saying before. You might recognize, you might say, well, there's not actually 2 factorial ways to arrange these, right? You might say switching those 2 R's around actually isn't a different arrangement. So you could recognize that and just do 7 factorial and then just divide by the 2 factorial for the identical M's, okay? That will give you the same result, okay? I'm going to choose to say, I'm just going to, like I said, I like to just pretend it doesn't matter that there's repeats and then worry about them at the end. So I'm going to do 2 factorial times 7 factorial, okay? Because again, 2 factorial ways to arrange within this group, and then 7 total things to arrange, including that group. So that gives us 2 factorial times 7 factorial, giving us 2 times 5,040, or 10,080. Whoops. 10,080. Okay, but we have way too many considered here because there are actually 2 identical R's and 2 identical M's, right? So 2 R's and 2 M's. Oh, I switched the color for R's and M's. So we need to take the 10,080 ways there are to arrange them, if the R's must be together, and divide by a factor of 2 factorial, because we have that many times too many arrangements that come from just swapping around the R's, and same for the M's. So this is 10,080 over 4, giving us 2,520. Okay, so again though, notice you could have just omitted this step, right? And that's totally okay, but then you don't want to divide by this 2 here. What I mean by that is, again, you might have recognized, you know what, I know that normally we would multiply by the number of ways to arrange these 2 within the group. But there's not actually 2 factorial ways to arrange them, so we really can just do 7 factorial is 5,040, right? But then when it comes time to deal with your repeats, you would need to recognize that you already dealt with this by excluding that 2 factorial, right? Which is totally fine, just keep track, right? So then you would have to do, okay, 5,040, we already dealt with the 2 factorial R's by not multiplying this by 2 factorial. So now I actually just need to divide by the 2 factorial M's, and you get the same result, 2,520. Okay, so generally speaking, like I said, deal with the conditions first, deal with the restrictions first, and then pretend the repeats don't matter until the end when it's time to divide them out because you have that factor too many unique arrangements that aren't actually unique. Okay, all right, one more example here. Let's finish this up. So how many ways can the letters in banana be arranged if it must begin with at least 2 A's? Okay, so that's important, at least 2. Let's just think about this. Deal with the restrictions first, okay, then worry about filling in the rest, B-A-N-A-N-A, okay. Now again, if there must be at least 2 A's, I'm going to choose to, again, deal with the repeats at the end. So I'm going to pretend it doesn't matter that all 3 A's are really the same, and I'll say we'll have 3 choices of A's, right? There are 3 A's to choose from. Okay, leaving us with, well, it has to start with at least 2 A's, so I've got to put another A here. I already put one here, so I've got 2 left. Okay, and those were my only conditions, but we got to think about what can go here now. It said at least 2 A's. So this could be an A, right? It's okay to have 3. That's still at least 2. It could also not be an A, right? That's still at least 2. So that means every letter that's left is available to us, right? It could be one of the A's or it could not be. That's fine. right? So we've used, 2 of the A's. We're left with B, A, N, N. So that's 4 letters. So 4 times 3 times 2 times 1, right? 3 A's to choose from. Must choose remaining A, or 1 remaining A. And then from then on out, we can do whatever we want, right? Choose any of the 4 we want. So what we've got here is 3 times 2 times 4 times 3 times 2 times 1, right? What that comes out to is 144. But are there actually 144 different ways? No, right? Because we have repetitions here. We have identical elements. So the n's, a factor of 2 times too many, right? Just from switching around the n's. And a factor of 6, which is 3 factorial too many, from just switching around our 3 a's. Okay, so we've got to divide those out. But, right, 3 a's and 2 n's. So the real answer, the real unique arrangements that you could actually tell apart, is going to be 144 factorial over 3 factorial, 2 factorial, which gives us 144 over 3 factorial is 3 times 2 times 1, so 6. 2 factorial is 2 times 1, so 2. So we've got 144 over 6 times 2, which is 12. So there are 12 unique arrangements where they begin with at least 2 A's. Now, B is similar sounding, but different enough, okay? Exactly 2 A's. This changes things. So same start here, B, A, N, A, N, A, okay? But now there are 3 A's, so I have 3 A's to choose from. I've got 3 options for what I can put here. Now the next one also needs to be an A. It has to start with exactly 2 A's. So this needs to be an A too. Must be an A. But can this letter now be any of the remaining 4 letters? No, it can't be. This cannot be an A, right? Because then it doesn't begin with exactly 2 A's. It would begin with 3 A's. Okay, so this must not be an A. Meaning that, if we think about it, we've used 2 of our A's. What we have left available to us is a B, an N, and an A, but we're not allowed to use that A. So we actually only have 3 choices to put here. We can put the B, the N, or the N. So we've got 3 choices to put there. Okay, now, how many do we have left to put here? Let's just keep track. We have B, A, N, A, N, A, right? We used 2 of the A's. Let's just say we used the B in that 3rd spot, right? Now in this spot, though, can it be an A? It can, right? It had to begin with exactly 2. So we did that. A, not an A. But now it can be an A again, because then it won't have begun with anything other than exactly 2 A's. So we actually kind of get a choice back here now, right? We could only use B and N here. Now we can use N or A, right? Assuming we use B there. So we've got 3 options again. We gained an option back on that next space. The A is back in play again. That's going to leave us with 2 letters after that and 1 letter after that. So multiplying this out, 3 times 2 times 3 times 3 times 2 times 1, what's that? That's 6 times 9 is 54 times 2 is 108. Okay, but what are we forgetting? The repeats, right? The identical elements. So, but we've got 3 A's and 2 N's. 3 A's, 2 N's. So we need to take that 108 different, quote-unquote, different ways, because a lot of them actually aren't different. In fact, a factor of 6, or 3 factorial, and a factor of 2 factorial. That's how many times too many we got. from thinking about all the different arrangements where we're really just switching around A's and switching around N's, and we wouldn't actually be able to tell the difference. So that's 108. 3 factorial times 2 factorial is 6 times 2. So 108 over 12, which gives us 9 unique arrangements. So actually not that many, because this has a lot of repeating letters, right? And there are a high percentage of the letters that are actually in the word. Okay, so that wraps up lesson 1 of our final unit. Okay, that is permutations. Permutations aren't going away, but that was the introduction and the main focus of this lesson. We will see them as we go. Okay, but that is the lesson focusing directly on permutations as its main focus. In the next lesson, we'll look at combinations. So now you can do your practice for this lesson, get comfortable with the permutations and the arrangements of different things where order matters. This is a good one to start out with, and then you can do the rest of them. Make sure you're reaching out to me with any questions, any concerns, anything you want to go over. I'm always happy to help.